Okay, I think we can start already. Pedro, can you please confirm that you can see my screen?
Yes, I can. I'm seeing the background of
Yes, that's the cover. That's the cover slide. Okay, thanks, Pedro. So welcome once again to this scientific requirement roadmap workshop from the EOatSEE project. I will make a short introduction now and explain a little bit of what we want to do today in this full day online session, and in which we really expect to have some interactions with the audience and trying to learn something about what should we be aiming for in our research for in the upcoming years. So today we are going to discuss coastal risks and emergency response and solutions that we can bring from Earth observation to support this kind of activity. And the reason to do that, as you all know, we are living into an urgent crisis. I'm showing some images here from the recent flooding that we had in South Brazil. As you can see, this is affecting more than 2 million people right now, and it's still running. This weekend was quite bad in terms of new rain, a lot of strong rain in a very complicated situation already. So this is ongoing disaster in a place that we were not used to see it in such intensity. So it's a typical compound event in terms of extreme sea level that is generated by both river discharge, so a lot of precipitation, really anomalous precipitation in a short span of time, but also very high seas due to the south wind that is blowing for a while. So, which of course limits the discharge of all this water from this coastal lagoon where the flooding is taking place. So that's the kind of problem that is becoming more and more frequent, and all these associated impacts that are so complicated for these populations that live in these low-lying coastal areas, but also for the ecosystems that are placed in these regions. So with that in mind, we have developed the EOatSEE project. So what is EOatSEE? It's Earth Observation Advanced Science Tools for Sea Level Extreme Events. This is a project funded by ESA. And you can see here the partnership. We are bringing together a numerical modeling community together with the Earth observation community, trying to provide a data-driven dynamic reconstruction of these extreme sea level events in different low-lying test regions to enhance the scientific understanding and the predictive capacity of such events, so that we can actually better prepare and support decision makers with the tools that they need to respond to this kind of disasters in the effective time. It's a project that has started in June 2023 and is to finish by this summer in Europe. And we are now in the final phase where we are trying to draft all these requirements for future research and development of tools. So the project is organized, it's really oriented by its scientific challenge, the scientific use cases that are developed in both the short term and the long-term temporal scales. So of course we are looking at forecast, short-term forecast, and try to have the predictability of this very complex compound event in order to enhance the capacity to deal with these events. But we also want to look in the long term about performing some risk and vulnerability assessment to understand where are the areas that are more prone to be impacted by such events, and how are these trends changing along the time in this changing climate that we are. And of course, for that, we need a lot of process understanding. We need to understand how these different processes are combined together and interact between erosion, flooding, river discharge, and how all these factors retroalimент themselves and actually drive our coastal risks. So we are performing these practical demonstrators in 6 different pilot areas with very different characteristics, but what they have in common is that they are all low-lying areas, thus prone to being impacted by extreme sea level events. As I said, the project has started almost 2 years ago, and we had a lot of work done. We had a first phase where we draft all requirements to be used as a baseline for developing all these products, all these solutions. We also, of course, gather a lot of solutions that are still being tested and are still experimental to work with them, scale it up, and have some subsets of this data benchmarked within our project. And currently, we are running this advanced Earth system science phase, where we are actually drafting a lot of new publications and technical reports on the results of such scientific demonstrators. But we are also promoting some transference of this technology to the society, talking to early adopters in each of those pilot areas, and trying to understand how they could use these solutions and what kind of value benefit they could extract from them. During the first phase, we actually retrieved a lot of different requirements, both from a literature review, from a similar workshop like this one that we're promoting today. We did something similar in the beginning of the project. It was actually quite successful. We had a lot of people coming from 40 different countries. But we also draft a lot of requirements from internal discussions that we had among our consortiums, because we, of course, have been collaborating with a lot of different scientists, both within the consortium, but also outside, associated scientists from the institutions that are member of the consortium. So this also helped us to draft a lot of different requirements. In the total, we had 8 different, very distinct user requirements. And from those, we pursued only the ones that were considered top priority, which were those 50 ones that were pursued during EOatSEE. And they were, of course, from all this phase of definition of requirement, we actually draft the main guidance of this scientific demonstrate for the project. So they are divided in these 3 different scientific challenges, trying to understand the drivers of these extreme sea level events and the nonlinear interactions among them. And then, of course, trying to make the connection with the morphology. So understanding both the hazards, but also their effects and the interaction with the coastal morphology. And finally, looking on the long term, trying to understand what are the tipping points for coastal impacts, and how can we actually understand where these environments will be affected in a way that cannot come back, cannot go to the original state. And of course, from these different scientific challenges, a lot of specific demonstrators were created, and that's exactly what we were presenting today. Today we are going to present the solutions that we deal with, and we are going to use several of these demonstrators as examples of what can be done and what we try to do with these tools. This is another summary table with a lot of the products that were generated. You see in the columns each of the pilot areas, and in the lines the different types of tools that were developed and implemented for each of them. And so you see that we actually went through a lot of different hazards, metocean data, but also a lot of data about the coastal morphology, and even indexes and models were actually implemented and deployed for different pilot areas. All this work is now resulting in different publications, as I said, and right now we are organizing a specific dedicated special issue for the project, which of course will not only include works from this project, but we are also inviting the scientific community to collaborate. So this is a good opportunity to do this. We had this specific special issue was opened for submission just last week. So you can actually use this QR code that I have here to connect to the website of the journal and find this special issue there where you can see your instructions, how can you collaborate, how can you submit your work. The idea here is to benchmark and to demonstrate what satellite data Earth observation can do for coastal risks, even if that requires the combination of this data with numerical models. But we really want to show the state of the art and what we can expect in the coming years in this type of technology. You can see that we have all these guest editors from different parts of the world, so we are expecting a very interesting and complete journal to be finished by, this is the final submission deadline. I'm almost sure that we have more time. So you can check the website using the QR code, and you'll see exactly all the details about this special issue. And of course, feel free to make questions about this as any other subject. So now let's talk about today. Yes, what we're going to do today, as you can see in the screen, we have a very long and complex agenda. We have a lot of very interesting presentations to do. And you can see this agenda again through this QR code, and you can explore it and see whatever you are more interested. As I said, we are going to promote practical demonstrations of the results that we got in our project, but also from other projects like ECFAS, ST Shores, Delta DPM, so different products coming from different projects. All of them have in common that they are solutions that are somehow related to Earth observations and are to be used in the coastal risks topic, most specifically for extreme sea level events. We are going to focus during the morning mostly about the long-term approach, so looking at tipping points, and during the afternoon, we are going to come back more for the short-term approach on predictability subjects. And we are going to run a couple surveys through the day, and we expect the participation of all of you. But of course, this is another link. This is another QR code for the first survey. But I also don't worry about this. I will also send these links through the chat here, and you will see that you can answer and participate. And of course, by the end of the morning, I will show these results, and we can have a good discussion. Typically, you should make your questions by the end of each presentations. So as you can see, we have 20 minutes, in some cases 15, but in some cases 20 minutes for the presentations, and we'll have some room for a couple questions, probably online. But of course, you can also write your questions in the chat, and the presenters will also be able to answer you in writing if there's not enough time during the presentations. And then by the end of the morning, like I said, we'll have a couple minutes to discuss, and if you have some pressing issues, we can come back to that. And by the end of the day, by the end of the afternoon, we have much more time to discuss and to talk. And so keep your questions, send your questions in the chat, or keep it for you to open your mic during these discussions, and we can actually interact. So once again, welcome. Please participate as much as you can. It's very important for us to receive this contribution from the community to understand what the scientific community is thinking about this topic and where you're going to place your effort for future research. We want to be a part of this, and I think we, as a group, we should be able to tackle this challenge of the changing climate and their impacts in the coastal zones. So without further ado, I will call up the first presentation, which will talk about the coastal total water level product that were developed within EOatSEE and show some practical applications of this product. So thank you all once again for participating, and welcome, and feel free to send your questions, send your inquiries anytime, please. We want to be as interactive as possible. Thank you very much, and we'll talk along the day. I will now pass the floor to Pedro Almeida, who is the principal investigator of EOatSEE, and we will start with this first presentation. So go ahead, Pedro, it's on you.
And it will just confirm that you can see my screen.
Yes, I confirm, Pedro. We can see it.
Okay, thank you. Good morning, everyone. Thank you for participating in this event. My name is Pedro Almeida. As you can see in the authors of this presentation, I'm representing someone else, Catarina Cecílio. And this work is a collaboration. So within the consortium, we have developed several contributions, scientific contributions and applications that were a result of collaboration, collaborative efforts of different teams. And in this case, together with the team of University of Bologna, we also developed this products and applications. So what I'm going to talk now in the next minutes, it's about the total water level at the coast. So we need, in order to manage the risks and vulnerabilities of extreme sea level events, we need to understand how the sea level at the coast behaves in the short term and in the long term. So this presentation, I will provide in the beginning a short context, and then I will describe the development that was performed and validation effort to compare this product with other existing datasets. And then Lorenzo will also present an application of this dataset, and we will present some of the next steps that we are working on. So extreme sea level in EOatSEE project, we addressed extreme sea level events in different components. So we are interested to improve our understanding and our capability to predict these events, considering their oceanic and atmospheric drivers. So understanding the nature of these compound events and how the nonlinear interactions take place. But at the same time, we also want to understand the effect of that at the coast. So understanding the interaction of these events with dynamic coastlines or with coastlines that have artificial defenses. And also, at the same time, this is all connected to understand the associated hazards. So as we know, extreme sea levels can promote flooding, erosion, and that hazards can interact by themselves as well with the upcoming extreme sea levels. So in order to be able to capture the short-term component, but also to assess in the long term these extreme sea level events, we need to be able to reconstruct the total water level at the coast. So that we call it total water level because it takes in consideration not only the global and regional aspects of sea level, but also local aspects, including storm surges and the wave-induced run-up component. So in order to be able to reconstruct this total water level, we have developed an approach that aims to deal with some of the identified problems. So in the short term, we want to be able to respond, or this can be applied to, for example, an early warning system that can warn when a specific event will go from a normal wave regime to an overtopping or a collision wave regime at the coast. So this is a type of application that we can use from this type of information. Or in the long term, if we want to avoid these type of scenarios of important hazards, and if we want to understand what will be the extreme condition in a certain year, we need to have a long-term time series so that we can compute extreme values such as return periods, or even to understand what has been the main cause of these events at a specific coastal site. Has been the combination of tides with waves, has been the storm surge. All of that needs to be assessed. So there are two components that can be, let's say, applied by using this total water level product. So our approach in the EOatSEE project has been to combine all these processes identified in this sketch. So we combined the sea level anomaly that contains regional and global aspects of variability of the sea level using satellite altimetry. And then we also we calculate the astronomical tides, the storm surge, and the wave run-up process all together give us the total water level at the coast. Our effort has been to put together a bunch of Python scripts that somehow can be seen as a containers of all these distinct process. So we can have the reconstruction of the sea level anomaly by having this first top box that process all the extract data product and converts and harmonize it in a way that can be joined with other variables. And for the other variables, we process it in the same way. So we have individual pipeline of processing for each of the variables, which means that if we want or if we have additional products or new products that we want to substitute some of this, we can easily include in this workflow. So at the end, basically, we have result hourly total water level data at any point at the coast in the world, but specifically we have the constraint at the moment of locations where extract data is present. So these are the present data sets we are using, as you can see in this table. So we use the extract L2P product for the sea level anomaly. This is a long track data along the coastlines of the world, and is produced by CTO Lagos. Then we have a number of IntCast data, such as the waves coming from the waveries, the CMEMS product, the dynamic atmospheric correction that we use to calculate the storm surge that is provided by Lagos and the CNRS and CLS. And additionally, we have also the FES model for the tides and the beach slope we are deriving from this past work developed by Deltares that provides this information at any point in the world. Some aspects that we developed also during the project. So we tried to combine the different tracks provided by the extract product in order to let's say, extend or increase the temporal resolution, but also to combine information that is provided by these different products in order to get, let's say, a more robust product at the coast. We tried to process it in a way that we collected information from different tracks that are passing through a specific region defined by a specific point of interest, and also avoiding to collect information that is potentially contaminated near the coast, where wave process can interact with the altimetric data, and there is no correction for that, or as well the process of interaction between the signal and land. Regarding the wave component, we use at the moment the IntCast data provided by waveries, and then calculating wave run-up and setup using traditional stock-down empirical parameterization. This parameterization was chosen because it offers three possibilities for three different types of beaches. So considering the surf scaling, which takes in consideration the slope of the coastal area. So we can, let's say, use the different parameterizations for these different types of beaches if we wish. The astronomical tides, as I mentioned, we use the PyFES toolbox that contains the ocean tides and loading tides together, and can calculate this information to any point in the world, in the coastal areas. The dynamic atmospheric corrections that is based on MOG2D barometric model, and that considers also the inverted barometric correction. And this is just an example of what we can, let's say, produce at the end, or what we can get. We can get the different components calculated to a specific point. We can calculate it from 1994 to 2021. It's a long time series. And that allows also to identify in a specific extreme sea level event what was the contribution, what was the magnitude of this different process. So we can identify in a relative percentage how much was the importance of the astronomical tides, how much was the contribution from storm surge, and all these different factors that contribute to the total water level at the coast. So this gives also a better understanding of this process in the short term, but then we can also look in the long term how these different processes are changing and behaving over the time and space. In EOatSEE, as Pedro presented before, we have a number of study sites, and particularly important of these sites is that they are vulnerable, they're typically low-lying environments, and they are in a distinct environments in terms of ocean and ocean basins and ocean basins, which give us also an interesting understanding how this type of analysis and products can behave in these different environments. So we have enclosed seas, open coasts, oceanic islands, all different and located in different locations as well. So we did a benchmark and validation effort. So we tried to compared the anomalies, the sea level anomalies, considering the monthly means. So we used the extract data by adding as well to the product the dynamic atmospheric correction. So basically we were comparing all the tidal residuals together. We compared that with the tidal gauges. And then we did also a benchmark. So we tried to compare this product, the sea level anomaly from extract, with the DUAX, which is a similar product, but is a graded product. So it has interpolation on it. And finally, we also compared the wave reads, so the wave data with the local wave buoys. So just a quick overview of this validation effort. For the sea level anomaly, so comparing the tidal residuals measured by the satellite with the tide gauge, we had an overall very good results with errors under 7 centimeters. And in this was observed in overall the sites with the better results on the Marshall Islands, so more oceanic environment. We had an interesting result when comparing with the gridded data. So we observed certain bias. The product was underestimating what was observed by the DUAX, and this was constant in all the sites. We are still trying to understand why this result was obtained, but we were confident by the comparisons with the tidal gauges. So it's giving us confidence that the product is correct. Regarding the waves, we also observed in general a good agreement, despite the fact that for the extreme waves, as you can see in this plot, there is a certain underestimation of the wave breeze product comparing with wave buoys. We also did an effort to compare this product with the field events, so qualitative comparison. So we recomputed the total water level at different coastal areas, and we compared with past events that we assessed the impact of extreme sea level events, and we could, let's say, confirm that the data set we produced was able to capture that specific events. So now Lorenzo will talk a little bit about an application that they developed, and I can just show the slides and Lorenzo will speak.
Yes, thanks, Pedro. So now I'll speak, as Pedro said, about this application of the Collab Atlantic data of total water level that we did. This is an application about the long-term analysis of this data. In particular, we apply a non-stationary extreme value analysis, that is to look at the statistics of the extremes, so return levels, but also to manage to understand how these extreme levels are changing in time. As an effect of the ongoing climate changes, we know that our extreme sea levels are changing, in particular due to the increase of the sea levels, to the sea level rise. But we'll see that in each of the focus areas, we have essentially a different story, and we have that the water levels are changing due to different reasons. In particular, we applied this technique, the transformed stationary extreme value analysis, which is at the same time well-based in the statistics and in the mathematics, but also relatively easy to implement and deploy. And is now having some success in our community. It is quite widespread and also being translated into other languages besides MATLAB, which was the original implementation, now is being translated to R and to Python. Next slide, please. So now we'll see focus area by focus area, the results of this analysis. In particular, here we can see how the total water levels are changing for the Marshall Islands. And in the figures, you can see on the left, the graphs return period, return level, where the red lines are the extremes of the total water levels. And also we see here the components of the total water level. In particular, the green lines are the run-up. The blue lines are the sea level anomalies. The black lines are the storm surge. The dashed line are the return levels at the beginning of the time series in the 1990s, while the continuous line are the return periods as estimated at the end of the period, so in 2021. So we can see that in the total water level, we have a significant increase in return levels. And we can also see that this change is significant. We can see this from the part of the figure on the right, where you can see on the top of the time series of the annual 99th percentile. We can see that there is a clear trend with the p-value close to 0, which means that from a mathematical point of view, from a statistical point of view, it is very significant. But then when we break down the change in the different components, we can see that this change in total water level is essentially driven by a change in sea level anomalies. So it is driven by the sea level rise in this case, because we can see that for the green signal, that is the run-up, we have essentially no change. And indeed, this is a change that is not significant from a statistical point of view. And also, the storm surges are low, and essentially the change in them is negligible. Next slide, please. This is what happens in Southern Adriatic. We can see that the story here is different. We still have a very clear and noticeable increase in the total water level. In the low return periods, we are like, in general, we have an increase of about 20 centimeters, that in this area is a lot. And when we break down this change in the different components, we see that this is essentially a sum of a projected increase in all the components. In particular, we can see a significant increase in the extreme wave run-up, in the extreme storm surge, and also in the sea level anomaly. So we can see that in this case, a positive change in sea level anomaly, which is driven by the sea level rise, combined also with positive trends in storm surge and in run-up. Next slide, please. This is what happens in the Northern Adriatic, and even if this area is very close to Southern Adriatic, the story is still a bit different. In particular, we can see that here we have a very significant increase in total water levels, which, by the way, reflects in places like Venice in the fact that we have higher and higher extreme sea levels that now, fortunately, in Venice don't reflect into impact because there is this new protection, this MOSE system, which is operational, which manages to protect Venice. But in terms of sea levels, this become higher and higher. We are breaking all the records. And this fact is reflected by this significant, very significant increase in total water level with the p-value close to 0. And we can see that in this increase in total water level, the projected increase in sea level anomaly, that is the part driven by the sea level rise, for the moment at least looks not, this component looks not statistically significant, probably because the sea level anomalies have the sea level rise, but also have other components, the sum up to it, that makes overall the change a bit noisy and not statistically significant. And instead, we see that we have a very strong increase in storm surge and also a significant increase in run-up, in wave run-up. Next slide, please. Now another time series. This is the one in Carcavelos, close to on the shores of Portugal. Here we notice that the total water level is dominated by the wave component. And we can see that even if it is not significant, here we have instead the negative trend in total water level. That is, we have a slight decrease in the total water level. Though it is, although this is not statistically significant on the extremes, it has a p-value close to 1, which means that is very non-significant. And this is due to the fact that we see the same trend, that is a decreasing trend in extreme wave run-up, which is also statistically non-significant. Which means that also here we have the sea level rise, and the increase in sea level anomalies is statistically significant with a p-value close to 0. However, the significant, the increase, the sea level rise in this area in terms of extreme sea levels is compensated by a decrease in wave run-up. Next slide. And finally, a development that is now we are close to submit a paper about this because we extended the transformed stationary approach to include also the study of joint extremes, which can be useful to understand, for example, the different contributes of, for example, sea level anomalies or wave run-up, but also can be useful, for example, to do Monte Carlo analysis, for example, to create a large number of hypothetical scenarios that are consistent with the climate at a given location in terms of contribution of the different constituents. And in particular, here you can see on the left the joint distribution between sea surface height and significant wave height at a certain location, and you can see that there is a strong coupling between the two, but if you want to recreate a realistic climate, you have to consider the coupling in the correct way. And on the right, you can see the coupling between the significant wave height at two locations at a certain distance, where the signal is clearly coupled because the hazard hits different locations at the same time. And so the risk is not statistically independent in the two locations. And you have to consider this when you do analysis of the risk, because the risk in general impacts simultaneously different areas. So this ends my brief presentation about this part of the analysis.
Thank you, Lorenzo. So just to finalize this presentation, the next steps, we are submitting a manuscript on the special issue that Pedro presented before on extreme sea level and coastal hazards on JAG. And also we wanted to replicate this approach at European coastlines. At the same time, we want also to bring a validation benchmarking analysis together with this new data set. And additional ongoing efforts, as Lorenzo presented as well, we are looking at improving this total water level product, or at least be able to integrate the dynamic behavior of land. So there is interactions of this process with coastal topography. As well, we want to be able to improve or assess the uncertainty of run-up at the coast, which is one of the most important variables for exposed areas. And we know that there are still work to be done regarding the parameterization of run-up at different environments. So thank you a lot for your attention, and we are happy to answer any additional questions that you have. And I will close this presentation now here.
Okay, thanks, Pedro. Actually, we are already running a little bit late, so I would ask you to hold your questions for the end, for the end of the morning. And in the meantime, I'm showing my screen again because I want to reinforce the invitation for you to answer this live poll. It's very important that we got some interactions from the public, because this is the main objective today, to get this feedback from the scientific community, to point out which are the needs for future research. So please, you can read this QR code, or you can also get into the links that I have sent in the chat. And once you answer, you can go through each slide, because you actually have different answers to make different questions here. So you just go to the bottom left corner and you navigate through the different questions. So I'll stop sharing now, and I'll invite Pedro again for the next presentation, which is also regarding
wait, I think Soraya is here.
Oh, okay, Soraya. Okay, thanks. Sorry for that. Okay, welcome, Soraya, and go ahead.
Good morning. I believe you already seen my screen.
We are seeing, but it's not on presentation mode, Soraya. It's
obviously not. Okay,
yes,
now it is.
No, it's correct. Soraya, just one note, if you can try to make it quick, a little bit quicker, because we are already running a bit late.
Okay, I will try. So I'm coming from Collab Plus Atlantic, and my presentation will be about extreme sea level events and coastal hazard tipping points under dynamic morphology. So, as already referred this morning, the extreme sea level events pose a major hazard to low-lying coastal communities, occasionally generating severe erosion, overtopping, backshore flooding, and structure destructions. Here I present some pictures of these situations in mainland Portugal. These events occur all along the Portuguese coastline from north to south. Almost every winter we have situations like this here. So when we talk about low-lying sandy beaches, the morphology is extremely dynamic. The morphology control and are controlled by the wave process, as the wave breaking, wave reforming the surf zone, the run-up and swash. And it also influences the impact of extreme sea level events on the coast. For a better understanding of the process and the impact of the morphology, this work focuses on two time scales. The short term, it facilitates the mitigation of extreme sea level events impacts on coastal communities. In this work, it examines the influence of beach profiles and submerged bars on extreme sea level events occurrence and identify the physical process responsible for these events. The other timescale in the long term, it enables to a more efficient coastal zone management by anticipating intervention needs. Here we estimate nourishment, longevity, and erosion tipping points, and we understand the impact of a dynamic profile on potential hazards. The study area is Caparica Beach. Caparica is located in the southern coastal region of the Tagus estuary. It is exposed to an energetic wave climate and a mesotidal regime. Also, due to its location, it's a very dynamic in terms of sediment transport, have severe problems of coastal erosion, and frequent episodes of overrush during coastal storm events. It is also a beach widely used for the population, for leisure, for bathing, for sports, do some jogging. So to keep these activities in the beach and to minimize the impacts of overrush and replace the sediment loss, frequency is a target of beach nourishments. These graphs show the beach nourishments performed since 2007, and during this period, 4.5 million of cubic meters were deposited in Caparica. So I will pass to the solutions developed in this in the scope of EOatSEE. In the short term, this work permits to predict extreme sea level events, understand the process responsible, and also the impact of the bathymetry in its occurrence. In the long term, permit to determine the morphological tipping points, the longevity of beach nourishments, and potential hazard regimes. Passing to the short term, in terms of the methodology, this approach combines satellite-derived bathymetry and the numerical model with the model X-Beach. The satellite-derived bathymetry use Sentinel-2 imagery with a spatial resolution of 10 meters. This technique with this part of the work was developed by Telespacio, our colleagues also in this project. The results of the satellite-derived bathymetry was validated with topobathymetry from COSMO from Portuguese Environment Agency. The COSMO is a monitoring program here in Portugal. The X-Beach implementation. We use 3 different beach profiles. When from 2014, it's considered our reference beach profile. And 2 other profiles derived from the satellite bathymetry, one from 2018 and other one from 2021. The 2018, it's a more vulnerable profile with low beach and lower submerged bars. And 2021 profile, it's a more robust beach profile. It is a profile after a beach nourishment in Caparica. The profiles correspond to this PO6 profile. In terms of wave conditions, 3 storms were simulated. These storms have significant impact on the Portuguese coast. The Hercules, storm from February 2017, and storm Emma. The model was previously validated and calibrated and validated in Garçon et al. 2023, and the same conditions were used for the 3 profiles to have exactly the same waves and only compare the different bathymetries. In this case, as outputs, we analyze the discharge to quantify overtopping events. the water level to study the process responsible for extreme sea level events, and to assess the influence of beach profile on the occurrence of these events. The validation of satellite-derived bathymetry shows very good results. The bathymetry can represent the bed forms observed in the measurements, as in the map, in the maps above, where in the left is the measured bathymetry, and on the right is the satellite-derived bathymetry. Also, in the profiles analyzed PO6 and PO7, the derived bathymetry can capture the submerged bars. We obtain root mean square errors below 1 meter in general for the results. We quantify the occurrence of overtopping events regarding the different profiles used and also for the different storm events simulated. In the case of Hercules storm, we identified 4 overtopping events for the reference bathymetry, 6 for the bathymetry formed for 2018, and 3 events for the bathymetry from 2021. In the case of the storm from February 2017, only 1 event was identified for the 3 bathymetries, and for storm Emma, none event was identified. Here we analyze the spectral analysis from the waves conditions, and we compare the dissipation of wave energy along the beach profile for each bathymetry. In the left, we have the bathymetry from 2014, in the middle, 2018, and in the right, the bathymetry from 2021. We observe that short waves, waves with a higher frequency, tend to be dissipated in the submerged bar, which acts as a filter, and pass longer waves with higher periods to the beach. The bathymetry have a highly control of the dissipation of waves along the beach profile, and are mainly the low frequency waves, the main responsible for the occurrence of these events. We also can see that the bathymetry from 2021 have less energy arriving to the beach, and because of it, also less events occur with this configuration. After we try to understand why in some situations overtopping events occurred and in other situations they don't. So here we have the black line, the low frequency waves, and at gray the high frequency waves, and blue the water depth in the base of the seawall. And in the red we have when the overtopping events occur. What we saw is that the occurrence of the overtopping events coincide with a sequence of higher low frequency waves that increase the water depth in the base of the seawall, and a higher wave comes and the event occurs. For example, in the bathymetry of 2021, the low frequency waves are lower comparatively to the other bathymetries, and lower events also occur. As final remarks in this approach, the bathymetry has a significant influence on the occurrence of extreme sea level events. The satellite derived bathymetry permits to have updated bathymetries whenever surveys are unavailable. This work reinforced the importance of having updated bathymetry and topography to have a good forecast of the events and a good understanding of the process. The model may be implemented to early warning systems and predict the occurrence of collision or overtopping regimes during storm events. Next, I pass to the long-term approach. In this case, we use the force model. Force is a reduced complexity model that means forecast coastal evolution. It was developed by Davidson 2020. This model is a cross-shore profile model, and the sediment transport is determined considering the magnitude of wave energy dissipation during wave breaking and the bed slope disequilibrium, where the model acts to restore the equilibrium. For this implementation, we use the total water level that it was described in the presentation before, and wave conditions from the Marine Copernicus, reanalysis from the global model. As outputs, we did the calibration and validation of the model. We determine erosion tipping points for nourishment interventions and assess the potential hazards considering dynamic beach profiles. In this case, we have the calibration. We simulated the period of 1.5 years from December 2019 and May 2021. And we test different pair of values, mainly K1 and K2, that are parameters responsible for the control the magnitude of the morphodynamic variability and the beach recovery parameter. We have root mean square errors between 29 centimeters and 56 centimeters for the pair of values used. The best results were with the K1 and K2 equal 0.005. And this pair of values will be used in the following for the following simulations and the following results. Next, we validate the volume evolution of the subaerial beach, comparing the force results with the volumes estimated by the measured profiles. They are represented by the red circles, and we saw that the volume was very stable. Does not occur a significant decrease or evolution of the volume. And this situation is because, as I referred before, this region is very dynamic and have a contribution of longitudinal drift that must not be neglected. So we had the parameter that represented the loss of sediment from longitudinal current. And then we have the new results, the full black line that represent that volume evolution, considering the decay of volume that is equal 140 square meters per year per meter of coast. Considering these results and considering that the model can predict quite well the evolution, the volume of a subaerial beach, we simulate the same with the profile without nourishment that correspond to the profile before the nourishment performed in 2024, that represent the beginning of this simulation. And in this case, we saw that the volume, considering the simulation without nourishment, beginning with a similar volume than when the nourishment from 2019 was performed. And here we permitted to establish a tipping point for nourishment intervention, which is the critical volume of the beach. And I have this is a satellite imagery from the Caparica Beach. Here in May 2019 is before the nourishment, and you can see the part of the beach is frequently submerged, and we don't have a dry beach. And here, after the nourishment in February 2020, we have a wider beach with dry beach for leisure and bathing use for the communities. Next, we estimate the potential hazard regimes considering the static level and dynamic level. These results are from the previous simulation with the nourishment. In this plot, the blue lines correspond to the total water level. The black squares are the occurrence of collision regime with a static level, and the red circles are the collision regime when we consider the dynamic level from the simulation. And we related these regimes with the Salinger regime quantification levels for potential hazard regimes. And the static regime, we obtain 22 occurrence of overtop of collision regimes. And when we consider the dynamic base bed level, we have the occurrence of 1015 collision regimes. Here in this picture of January 2029, we see that the beach is frequently under submerged in most part of the time. Here in this, mainly in the high water, and with the extreme events with this configuration, probably this will occur again with the overwash regime. So, as final remarks, the force have the potential to predict long-term beach nourishment behavior, and may be possible to test different designs nourishment. These will be tested. Total water level applying the storm impact scale of Salinger permits to predict the occurrence of extreme sea level events and the potential locals of on a potential early warning system. And with the numerical modeling, it permits to have accurate results. For longer term simulations, the model permits to assess the impact of sea level rise on coastal evolution and the natural variability due to forcing wave forcing. And that's all. Thank you very much.
Okay, thanks, Soraya, for your great presentation. It's a lot of science for us. So let's move directly to our next presenter. In the meantime, I just remind you, let's try to answer our live poll. I will send the links again. We are adding more questions which are related to these last products that are being presented. So please welcome our next presenter, our colleague from Deltares, Matheus Gowen, will talk a little bit about how EO can be applied in a remote Pacific island. So go ahead, Matheus, you have the floor. We don't hear you. I'm not sure you're speaking. Mm. We're not muted. Yeah, nothing else is missing. Unfortunately, we cannot hear Matthias, but go ahead and try to do whatever you need, and we'll wait a couple minutes.
Can you hear me now?
Yes, now we can hear you.
Perfect.
Loud and
Okay.
clear. This is
Just
good.
did a quick
Yeah, forget
headphone.
about the headphones. No way, no worries. You have a good audio now. You're not in presentation mode, Matthias. If you can just make it larger.
I will. So thanks
Perfect.
for
Go
having
ahead.
me, of course, Pedro. I will tell you something about what we did with Earth observation data at Majuro Atoll, which is a remote island in the Pacific. And I just want to do a very quick summary of what actually goals were in this case for within EOatSEE. So by the way, so in the lower parts you see Majuro and how it looks when the island starts to flood. So we wanted to evaluate Earth observation data for environments, specifically so for coastal inundation studies. And in this case, we focused on EO-derived water levels, but also EO-derived topography and bathymetry. And in this case, so we were looking at Majuro Atoll, where we had some kind of the nice benefit of having good in situ data. And this is normally not, or usually not the case in the Pacific region. But here we could really test what the quality was of the EO data. Let me directly jump into the water levels that we used. So in this case, we used water levels from the in situ gauge, and we compared them to water levels we got from the Extract EO merged satellite bathymetry product. And what you see here on the left is, so you see in the middle, you see Majuro Atoll, and this green star is the gauge that we had, and the red dots are the satellite tracks that we use to derive, or that we use to merge all the EO water levels. And what you see on the lower right is how these two compared if you plot them in a time series. So you see the time series from 1992 to 2020, about 2020, and the red dots are the extract data, and kind of this dense black line is the water levels from the gauge. And what you see is, so generally the red dots seem to follow the black line quite well, but it's way more, it's less dense. So we don't have as much data as from the water level gauge. And this means we have an observation every 1 to 10 days, kind of, if you for the general picture. So how does it look if we look at the accuracy? So the water level data were actually quite good. So there's generally a good accuracy. There's a good correlation, so a very high Pearson coefficient. Also, the RMSE was quite low, so it was 5 centimeters. And even this 5 centimeters was a bit debatable because of the location where the gauge was situated, which was in a lagoon. And in a lagoon, we could expect some a little higher water levels, especially in the higher end. So we had good accuracy, but what is most important in these vulnerability studies is that we get the extremes right, because the extremes are used to really look at island inundation. And here the story changes a bit. So the extreme values, they were underestimated a bit, and this is exactly due to this data intermittency, though. So this these measurements that we only have once every 1 to 10 days from. On the left-hand side, you see the extreme values derived from the water level gauge, and on the right-hand side, you see them from satellite and from extract. And so the vertical axes are exactly the same in both plots. And what you see is, so the gradient is perfect. We kind of fit a correct gradient for the extremes, but it's generally about 20 centimeters lower. And this is a very known artifact, actually, that you get looking at extremes from EO. So this is kind of expected, but important to know. So the conclusions are the individual measurements are good, but the sparsity of these measurements of the EO data means that we underestimate the extreme values by about 20 centimeters. So and then the question is, of course, is this a problem when we look at hazard assessments? The next part that we looked at was at the topography and the bathymetry from Earth observation data. And just as a bit of background, so for the ground truth, in this case, we had very high resolution LiDAR data and also a nice merge product from the USGS for the bathymetry. And in this case, for the topography and the bathymetry from Earth observation, those were derived from high resolution World View 2 images. So a stereo image, which means that you have two images which you can use to derive a relief. And this was about $45,000 or dollars for 10 by 10 kilometers of area. And that's the image you see to the bottom right. The horizontal resolution is about 1.8 meters, and we derived in this case, CLS derived the topography via photogrammetry, and the bathymetry was derived through color analysis. Now, how do these data look? That's, of course, the most interesting part. To the bottom left, you see the ground truth data, and now to the bottom right, you see the derived or kind of also the mosaic of the topography and the bathymetry from EO derived from World View 2. And just as a general picture, I want to show this here. So I think they look quite similar, which is nice. I will show you how these data have looked before when we didn't have those kinds of EO data. Just have a quick look also at the difference. So for the topography, the difference for the area we were looking at was about 1.17 meters, which is debatable how much that is, let's say it that way. So the problem with these islands is they're very low lying. So it's important that you have the bathymetry right. So 1.17 would actually be a lot, but in this case, a lot of the error also stems from kind of a quite smooth estimate close to the waterline, which happens because you can't do any photogrammetry beyond the waterline. So in this case, one ground control point was just one ground control point was actually needed also to reference the EO data correctly, which I think is quite a strong point. And then looking at the submerged topobathymetric product, the RMSE increases a lot. So the bathymetry was actually quite difficult to invert from the satellite data. And the main issue here is that there's a very high albedo in the Pacific. It's especially, close to the equator, sorry. So this made the color analysis quite challenging. And you see that also, so I'll just want to be sure that you also see that the difference axes are a bit different. So on the left-hand side goes to 1 meter, on the right-hand side goes to 3. So the topography is really good, but you see that the bathymetry has lesser accuracy. Yeah, so I just did. And then, well, the interesting parts, of course, what are the consequences of these water level and also the topobathymetric artifacts on our flood maps? So what was the approach to produce these flood maps? We ran simplified versions of models that were set up actually quite recently for a big coastal vulnerability study at Majuro. We reran them, and in this case, we started to successively substitute EO data to see what the effects were on the flood maps. And then finally, we looked also at we compared these flood maps to current and future conditions. So first, I want to look at the water levels from Earth observation. I want to just remind you again, so where we had this artifact of 20 centimeter lower water levels. So if we look at the effect for current conditions, so on the left-hand side, you see the ground truth bathymetry with the ground truth water levels. And this is kind of a flood map that you then get. And on the right-hand side, you see also the ground truth bathymetry, but then where we use the EO water levels. So just to look at the effect of the water levels. And what you see is that these 20 centimeters actually make quite a difference. And this kind of shows how sensitive these low-lying islands are. So having a difference of 20 centimeters already can have quite a big impact on your flood maps. This has actually more implications because this also means that the general data accuracy is important. So also referencing things correctly in reference heights already has a big impact on your flood. So we get less flooding using water levels from EO for current conditions.
I'm sorry, Matthijs, something happened with your sound because now it became just in the last 10 seconds, it became very low. I'm not sure. Can you try again?
Hello?
Yes, I can hear you.
Yeah. Okay, perfect.
Yes, perfect. Thanks.
Okay, so for sea level rise scenarios, actually the impact of these errors in EO start to be less important. But that's just because the sea level rise scenarios already have a big impact. So as I just showed you before with these 20 centimeters, if you impose sea level rise of 1 meter, almost the entire island floods. And then it doesn't matter a lot whether you are wrong in your water levels by 20 centimeters. Presentation has frozen. Let's see. No. I don't know what has happened, but my presentation just froze. I can't even get out of it. That's weird. Let's see if I can make it out of it somehow. I'll just try to reshare. Let's see if this works.
Yeah, maybe.
Let's try again. Can you see it again?
I can see it, but not in presentation mode. No, it's just showing the slides.
Weird, it doesn't. Okay,
Yeah.
now.
Perfect.
Okay, so sorry for that. I'll just go back to where we were. So the kind of just quick recap. So there's you get less flooding using EO water levels, but for sea level rise scenarios, it becomes less important. In this for an error margin of 20 centimeters. So we also then did. Oh wait, sorry. What is interesting now is we're going to look at the topography and the bathymetry, and what I think is very to show is what quality of data was before we had these kinds of EO data. And then I want you to focus on these left column plots. This is merit data. This is what we are usually confronted
Yeah, no, I'm not sure what happens, Matthias, but unfortunately your sound just goes lower and lower, and then it somehow disappears. You just connect again the headphone.
So again?
Yes, now it's perfect again.
Oh, I'll try to be quick, and hopefully my computer stays in this mode. So the merit data on the left-hand side that you see here, that's what we usually confronted with, and I just think that it's nice to know kind of how much better these EO data were in this case that we could use. And what I'm now going to show you is 3 different cases. So the reference data where we use these ground truth data with LiDAR and USGS, of LiDAR and USGS data. And then the case where we replace the LiDAR data for the EO topography. Then lastly, where we replace both the topography and the bathymetry with EO data. So on the left-hand side, you see the reference data, and then kind of on the right-hand side, you see where we use the EO topography only, and then on the right-hand side with also the EO bathymetry. And this is kind of a low forcing, what you see here. So there's no real flooding of the island, and all plots are similar. So the main thing that kind of appears here is that you see that there's more run-up, a bit more drowning of the coastline in the EO, in the simulations using EO topography and bathymetry, and that's because they are smoother. What happens with a medium forcing? Then you get these kinds of pictures where you get a little bit of island flooding. And then when you look, in this case, in the middle at the situation where you use EO topography, parts of the flooding are also correct when we use the EO data. But that means parts. So for example, here on the right-hand side, which this right-hand tip is called Uliga, there the EO data predict quite some flooding, whereas in the reference data, there's no flooding or very little flooding. And then again, when we have a high forcing, all the simulations start to align quite well, and that's simply because the entire island starts to flood. So here's the kind of the conclusion here is that so using EO topography or EO topography with bathymetries actually gives quite similar results. But generally, we get a little bit more flooding using the EO topobathymetry data compared to the reference. So that is the presentation. I hope you could hear it now.
Yes, of course. Thanks very much, Matthias. This was very interesting. As you know, we've discussed it before, but we all were very excited with these good results in such a challenging environment. We all know that you had a lot of challenges regarding the bottom reflection, the different albedo that we had in this location. So when Telespacio derived this bathymetry, they had a lot of challenges. But I guess in the end, you actually got very interesting results.
Yeah. I'm sorry, but I also really have to jump out now, Pedro.
No worries, Matthias. I see there's no questions right now in the chat, so I'll make sure to relate any questions we have to you, and we'll come back to this to the people that make these questions, and we'll provide the answers as soon as we can. So thanks again very much for your presentations, and let's go. Let's continue with the workshop.
Yes. Bye-bye.
Bye-bye. So actually now for our next presentation is also from a colleague from Deltares, is from Martin Pronk.
Yes, hello.
Hello, good morning. And he will talk about the new Delta DTM digital elevation model. So I think this is going to be also very exciting. This is not something that was produced in EOatSEE, so it's just something that we are glad to have the opportunity of hear about this very interesting new product that has become available from Deltares. So go ahead.
I will share my screen, yes.
Of course.
Is my screen visible?
Yes, yes, perfect.
Okay, so this is a combo presentation. Indeed, Delta DTM, the elevation model I'm presenting, is an external development, and Marieke, who's in the EOatSEE project, will tell a little bit about her part of that afterwards. So let's start with Delta DTM. So for those of you who don't know yet, last March, I believe, we finally published a new global coastal digital elevation model, specifically a terrain model, in Nature Scientific Data. So this is an open data set that everyone can use, CC BY license. And I'll tell you a little bit about why we made this data set and how we did that. So as we've seen also in, I think, the whole of Matthijs' presentation just before was about elevation and how better elevation data impacts your analyses, which is also something that Marieke will show basically later on in this presentation. And ideally, we have the best elevation data source, and that's LiDAR. So that's a laser, and often we use that from airplanes. And then you get national elevation models, or only for small project areas. And LiDAR has the highest accuracy, and it gets that accuracy mostly by actually penetrating canopy or measuring in between buildings. So then you get an elevation model of the actual terrain. On the right-hand side is an example for an area in Indonesia, a low-lying area. It's a plantation next to the coast. And there's loads of details to see here, small irrigation canals. There's some peat domes. And this is what you want if you want to do any analysis based on an elevation, so hydrology models, etc. Unfortunately, LiDAR is expensive. So the availability of actually having LiDAR elevation models is pretty bad. So this is a screenshot from the Open Topography web portal. And all the dots here are basically LiDAR sources. I've added a few pink ones of the national models available in Europe. And it's growing, but what you see is, especially in the global south, in South America and Africa, there's no LiDAR data sets. These dots are probably, it's a volcano or an earthquake data set, so collected for a specific project on a very small region. But in the rest of the world, especially, let's say, Southeast Asia, where risk for sea level rise is quite high, we don't have good elevation data. So we're not able to do good impact analysis there. So what you fall back on are global elevation models, and they're not based on radar. So radar satellites. And we've seen them. And Matthijs actually also presented one, Merit. It's based on SOTM. And then many others. Recently, you got the Tandemix missions. There's also data based on stereo photogrammetry. But all these models, they do not fully penetrate the canopy. So they either bounce off the top of the canopy or they penetrate the upper part. So you get a large vegetation bias in these global elevation models. And the same happens with urban areas where they bounce off the roof of buildings. And they might measure in between a little bit between the houses, but they don't really reach the ground. So an example here on the right-hand side again, this is I believe, the Indonesia national model for the same area I just showed you. So here you see no small irrigation canals anymore. You see a lot of vegetation effect. Everything that's dark red is essentially forested area, and it's not the terrain. So of course, this is well known, and much research have gone into this. Merit already tries to correct for canopy, but not for urban areas. And recently, FABDEM is very well known, but it's only for research purposes. Is it freely available? It's otherwise commercially. They all try to correct this digital surface, so the canopy and buildings. They try to correct for the effect and get the terrain. So this is something we've done now as well, because we still saw an opportunity here, and that opportunity is based on new remote sensing data, mostly based on LiDAR remote sensing data. There are two missions from NASA, ISAT-2 and JEDI, and they both have been launched at the end of 2018. So roughly from 2019 on, we have these satellite LiDAR data. And this data is really accurate, but it's sparse data. Just like the data that Matthijs showed you in terms of water level measurements, they're point measurements, and that means you get lines. So there's a nice diagram here from EOatSEE from their website, and you can see it's a LiDAR, and it's basically a sort of brush across the earth, and you get a lot of lines. So again, for the same area in Indonesia, I've plotted here the EOatSEE data points. And you see that if you have data, you have a nice track, you can clearly see the terrain profile. There is some noise in there. Maybe it does measure the top of trees sometimes, but it can be filtered quite nicely. And then you have the terrain again. The trouble is, of course, that this is not 30 meter. You have huge gaps to fill. So what we did is basically combine these two data sets to get to delta DTM. So we have a Copernicus DEM and the EOatSEE and JEDI data. And then we get delta DTM, and it's a 30-meter global coastal terrain model. We published about this. It's also an open access paper linked here. And our coastal definition is up to 10 meters above the EGM 2008 GEOat model, which is roughly global mean sea level. So this is a first version. Again, this is open data. I'm currently working on a version 1.1 that hopefully goes to 20 meters, basically based on popular request. And I'm thinking about making a version 2 that would be a global data set, not just coastal, but that will be in the far future. So a little bit about how I generated this model. Essentially, we take Copernicus DEM, which itself is based on TandemX. So that's a radar-based model. I've put it here on the top left image in this diagram, and you can see a lot of vegetation effects in there. So that needs to be corrected for. And what we do here, based on EOatSEE and JEDI data, we classify this raster. So for each pixel in this raster, we determine whether it's a terrain measurement or not. Basically, if you have a EOatSEE terrain measurement nearby, you can assume some things about the slope of the terrain. And then if a Copernicus DEM pixel is really high, let's say 10 meters higher, well, it's only 100 meters away, you can say this is unrealistic and it's non-terrain. So in the middle picture here, middle left, we're left with only the classified terrain pixels, and we can interpolate the remaining gaps, and then we arrive at delta DTM. And this works quite well in the low-lying areas, the flat areas of the world, the deltas, hence also the name. Delta DTM, of course, Deltaris also plays a role in there. In terms of accuracy, at the moment, compared to the other data sets, so NASA DEM, Copernicus DEM, Merit, Coastal DEM, FAB DEM, Diluvium DEM, all are existing global elevation models. Some of them are corrected. We have the highest accuracy at the moment with delta DTM. So we have a root mean square error of only 0.74 meters when we validate it against several airborne LiDAR DTMs spread across the world. And this is not just boasting. Having a low RMSE is really important if you want to do assessments later on. So I think this might be even the most important picture for delta DTM. If you want to, let's say, model sea level rise impacts, and you want to do that in a, let's say, a scenario of 1 meter, so compared to nothing, 0 to 1 meter, it's an increment of 1 meter. If you want to be quite certain about that analysis, you need to have an elevation model that has an error way lower than that 1 meter increment. So based on the GASH 2018 paper, you can plot that relationship, and you will see that for the 1 meter line that I plotted here, if you want to be a bit confident about the result, you need to have a root mean square error far below 1 meter. Actually, I would say you would go to half a meter of RMSE before it becomes acceptable. And you see that even delta DTM with 0.74 meter RMSE is only half 50% confidence you get for 1 meter increments. At a 2-meter increment, you're at above 80% confidence, and that's a nice threshold. You can see that other elevation models with higher root mean square errors are even, well, less confident in modeling small steps like sea level rise. So this is really important to keep in mind when you use global elevation models. That being said, I'm happy that delta DTM is the most accurate thus far. I'm aiming at improving it further to get this graph even better. And with that, I'd like to hand over this presentation to Marieke, who will tell a little bit about the Dutch scientific case in the EOatSEE project.
Yeah, thanks, Martin. You can do the slides, yes?
Sure.
Okay, thanks. Yes, I want to keep it short, but what is nice here, what we see here very well, is we see this global potential of remote sensing, I think, or near global. I think this is really, I would say, one of the key features of remote sensing, which we're all interested. Also, what we're interested in at Altaris, we often test locally and then try to scale up to a global product. But now I go back a little bit to the Dutch coast, and it is a little bit about these accuracies and how we should deal with this. So maybe you can show the next slide. So what we've made before is a demonstrator. So it is not meant for management decisions yet, but a demonstrator where we use the terms that you've heard before, the total water level, and you heard about the wave statistics. We get that from, so the total water level, we get it from GTSM, so a model, which is global, by the way. And we also use the wave statistics from ERA 5, and we were interested in a significant wave height and also peak period. And at the depth of closure, so that's let's say at the depth where there's still a lot of it's the boundary between that there's a lot of activity in the nearshore sediment and not so much, which is at the Dutch coast at about 10 meters. And we also looked at the impact in a similar way as what has been presented before. So it's Stockton. To look, to take the measurements closer to the coast and look at what it actually means for this case for the sandy coast. In this case, the coastal dunes. Next slide. And what you then get is if you have such a model and you also use a Broun model to look into let's say the not only the vertical levels of the wave run up with respect to the top of the dune, but you also try to say at least something about these changes in the sediment. So also in a lateral way, you start to get into this kind of scenarios which you can run. With GTSM we can also add global sea level scenarios, so add like 0.5 meter, 1 meter, 100 meter scenarios, 1 in 100 years return period, these kind of things. And we can start modeling and say something about the beach profile. Are the dunes in this simulation, are they still high enough? And are they also broad enough to not go into a different regime? So a Salinger regime. So for example, go into an Ohuas regime. These kind of simulations we can do, and we could do also before EOatSEE. Next slide, please. What we use there are actually very good, so very detailed profiles that we have, and they are based on airborne, like what Maarten just presented, airborne LiDAR measurements, and also multi-beam transects that have been multi-beam measurements that have been combined for the Dutch coast, and we have quite a lot of these measurements as well. So this is again something. It's something about the quality of the measures that we need for such a prediction. And in the prediction, I must say there are many assumptions. It's a very simplified model. Okay, next slide. What we did is we also, I think this has been presented before, I'll go fast, but we also compared the tides gauge measurements against the total water level measurements. These are early ones that you see here. And we do see quite a lot of scatter. That is because in our area, a search range was was taken of 2 degrees. And it's quite an, in this area there's an amphitromic point in there. The bathymetry is very shallow. This is the most difficult area that you can have, in the sense that it's really varied. So the variation inside is huge. So that makes it actually quite a complex case for altimetry, I would say. Okay, this is also, next slide, please. It's also the same for if you want to use it for significant wave height statistics, and we need these statistics to calculate return periods. That's clear. We have also looked here at the 2 products, so which was presented also before, also the ERA5 and the WAVRES data. And what we actually see is that ERA5 seems to do a little bit better, also for the high peaks, for the significant wave height, and then WAVRES seems to do maybe a little bit better for the peak period, but look at the scatter that you have. I mean, this is really problematic. Okay, next slide. What was very nice of EOatSEE is that we also got some land cover, land use data, which we could verify as well. And of course, that's very interesting for the impact that you have. So you want to know something about the topography. You want to know whether there is any chance for the dunes to move laterally. So if there's room, space for that. And you also want to know for the impact, okay, is what kind of area is behind it. So possibly with a lot of sea level rise, we could agree that some of the natural areas get flooded, as long as we have like a huge dune and natural area behind it, and we maintain this high inner dunes. It's one of the things we can think of for future coastal defense. Next slide. So what EOatSEE has given us is that before there are always hesitations about what can we do with remote sensing. Are the time series long enough? And I think we tackled this, or we tried to tackle this at EOatSEE, where we mostly use this extract, but also there within other products, you have these intercalibrated measurements from the altimeters, which makes it possible to get a large time series. Well, the other thing is that we always say we want to have the temporal resolution should be higher. Yeah? Again, we do this by using this search area, and that works sometimes very well. And in the search area of the 2 degrees that I talked about, that works sometimes very well. For example, for Marshall Islands, it doesn't work so well for the Dutch coast, and I explained why. What can then be developed? Possibly also from the remote sensing community. Well, what is interesting there is that if you would go to constellations of altimeters, then you could possibly increase this temporal resolution. So this is something to think about for the future. Now, the other thing that is that we want to, the altimeters, they end offshore. We are interested in the processes to bring them closer to the coast where there is the impact. There's a lot of uncertainty there still, certainly in the model that the empirical model that I use, but also in others. It's interesting for us to get altimeter data close to the coast. So fully focused SAR and also SWOT might possibly also help a bit here. And other things that we've been checking already, also with TU Delft, is to see if we can do something with using modeling to bring it closer to the coast, but also machine learning. Next slide. The other thing is this, this based on the temporal resolution, so very close to the coast. So what we've seen is this, we're really happy with this global DTM. But if you compare it to the camera images, so the Argus data that more people's interested in more for dynamics we're used to, we need more. So again, possibly data from constellations where we get, let's say, more sampling in time, and also this high resolution that is required. Maybe that is a possibility there. And also again here, we can think of the modeling to fill some of these gaps. If we look at risks, then I think this land cover land use image has shown to be very, very interesting. And what I think is also something that Maarten will also start working on in the future is we're really interested in protection structures as well. So mapping of protection studies. So that's all from my side.
Perfect. Thanks, Mahika. Thanks very much for this practical example of benchmarking of this very novel product, which I think it's going to be very useful. And I'm sure in the coming months, we will you guys will get a lot of feedback regarding this product and its applicability in the real scenarios. So moving on with this webinar, I'm sorry, but we are running a little bit late. Anyway, I don't see any questions in the chat right now. So let's go over to the next presentation. So we are going to invite now another outsider from our project. So another invited speaker that will show also a novel solution that was recently developed. So I will pass the floor now for Rafael Almar. Rafael is the coordinator responsible for the littoral group within LAGOS, the Laboratory of Space Geophysical and Oceanographic Studies in France. So go ahead, Rafael, please feel free to share your screen and
okay, thank you.
Enlighten us.
Okay, can you see my screen?
Yes, now it's perfect.
Okay, so thanks for the invitation in this project. I don't see the yeah, now it's okay. So I think it's very in line with the previous presentations. I will present what we are developing in our group, like on the coastal topobathymetry from space, in collaboration with like colleagues from CNES, the French Space Agency, and the French Navy, and LAGOS, the academic lab, where I am. And first, okay, it was said before, but there is we can estimate the sea level with a millimeter accuracy with altimeter, for example, but we have meters of error on topography. Well, maybe a bit less, but meters in general, and on bathymetry the same. And most of the coasts have never been like surveyed, or when it's done, in general, it can be like decade old, or even more. So most of the bathymetry and topography are outdated. And you can see like on these two sites, like some profiles, this study is already like 3 years old. So we didn't include like the new Delta RS product, for example, with ISAT2, etc. But you can see that, okay, the dune is not super well captured. So in terms of coastal flooding, this has a massive impact. So the uncertainty and morphology is actually the most important uncertainty in coastal flooding, more than hydrodynamic model, for example, or sea level observations. So we developed a methodology that we were developing for previously for drones or video, that we applied and implemented on satellite observation. This is based on waves. So we capture waves and we inverse bathymetry. So this potentially works in like turbid areas and other type of coast where the bottom is not is difficult to see. And this method works on most of the optical sensors, like Sentinel-2 mission, Venus, Pleiades, Gillian Planet, and the future like CNES and Airbus satellite COS3D. The code will be released like open source in 2024. And we already did like a world atlas, coastal atlas, and it's available for test. And we are now working on a new atlas that will be publicly released, the data. And like everybody, we are going toward the dynamic evolution of the coast. So again, this is done as part of a work between LAGOS, IRD, SHOM, and CNES. So this method work. You can see on the upper left panel, like it's a Sentinel-2 image with the different color bands that are acquired with certain delta t that reach like 1 second. So you can see a plane with the red, green, and blue bands that are not at the same position. You can see propagation of the plane. So that's what we apply to wave propagation. And then we apply like a polar transformation based on radon transform, FFT or correlation to capture wave celerity. We capture wavelengths, and based on the linear wave dispersion, we can inverse bathymetry. That's basically how the method works. What we saw, like other groups, that like the timing of the different Sentinel-2 spectral band is not perfectly accurate. So this was reprocessed by a CNES group. And by doing this reprocessing, actually, we could really improve the accuracy we have on the bathymetry estimation, and so on wave speed, and then finally on bathymetry. You can see here the impact of such a correction. So this reached like 10% of the bathymetry if you use ESA or the reprocessed timing. And then the product is based on like individual estimation can be noisy, of course. So we do like a multi-date composite. There are different methods, and then we have an automatic chain to test the different criteria from International Hydrographic Organization, IHO, and with different classes. And we see where the satellite-derived product pass the different classes. Our first regional test was in West Africa for Sean, the French Navy. It was the first test also for the HPC massive implementation at regional scale, and you can see the improvement compared of S2 Shore compared with JEPCO in Guinea-Bissau, where you have a lot of turbid waters and channels that don't appear in JEPCO basically. So it was nice to see the improvement. And in this particular area, by having this improvement, we could test also the impact on hydrodynamic model, like basically a CROCO here, a 3D model. So you have the JEPCO bathymetry on top left, and then S2 Shores and CMAP, which is like in situ measurement. And the tide was improved when using the fine scale of S2 Shores compared with JEPCO alone. Now we went in 2021 to global processing. So this again was a massive. It was more a test for massive HPC computing by running like tens of thousands of Sentinel-2 tiles. So the CNES colleagues work a lot on optimizing the code and also the big run. And we did a composite, multi-date composite, and we have a few showcase, a regional showcase in this slide. And here a comparison, a correlation basically with, well, there's no global bathymetry that we trust. So it was just a correlation, basic correlation with JEPCO. So we can see more or less where they match or not. But we hope to be better than JEPCO. So it's not the best reference. And on the bottom, you have a comparison with a SHOM, so surveys on small areas. And now, okay, bathymetry is something, but we cannot limit ourselves to the submerged area. So it's important to move to the coastal morphology, which has a part underwater, the bathymetry, but also the topography. And nowadays, like the satellite missions such as Pleiad and Pianeo are able to get that, like the continuum topobathymetry. And here is a showcase of a rapidly evolving morphology, the sunspit of Langue de Barbarie in Senegal at Saint-Louis. And we can see like the several DEMs obtained at different moments. So we can capture really an evolution of the coastal morphology, which is quite interesting, particularly in these rapidly changing areas. And here it's in Sydney, Narrabeen, in Australia. It's a showcase of, with a single pass of Pleiad, we acquire different images and we can reconstruct like this continuum with still a bit of error. And we hope the new missions will help to reduce this error. And here also at the most surveyed site in the world, which is Duck in North Carolina in the USA. And we could like really get for the, I think it's like for the first time also in Matthijs' work in Cabreton, but the sandbar. So which means we are now accurate enough to get that. This was done with the Chinese Jilin mission with and 20-second video from space. So this video from space are really the new border of what we can do in terms of accuracy, because we can have up to 1 minute of video. And also another border is like the resolution. And with Pleiad Neo, this is an image from Pleiad Neo, the new mission from CNES and Airbus. The resolution has been reduced, and now we can have a very fine topography resolution using photogrammetry, stereophotogrammetry, and we can get the difference with Pleiad. That with Pleiad we could get beach and dune. Now it's accurate enough to get also coastal protections and dikes, which is important for coastal flooding models. And the next steps are like to use this satellite-derived DEMs in coastal flooding scenarios and modeling, as I just said, but also to capture the morphological evolution of the landscape continuum. So now we have meters of error, so we have to capture like morphological evolution larger than meters, but this will reduce in the future to capture like finer evolutions. So thanks a lot for listening.
Thanks, Rafael. This was quite a short but intense showcase of a lot of new solutions and also some prospect for the future. I agree that we are making way very quickly to have more sophisticated and actually useful products for coastal risks. So guess we're almost there. So thanks again, Rafael. Once again, I don't see questions, but we might get them later. And of course, if you cannot stay, we can relay them to you, and we'll make sure to answer them. So again, right now I will progress with the workshop, and I will invite another external presentation from ECFA's project, which is maybe some more practical application of all this data that we are being able to produce from the satellite imagery in the actual flood scenarios. So please welcome for this presentation Claire Dufault from CLS France. She will be giving this short presentation on the main outcomes of this new project that has just finished. So
okay.
Claire,
Thank you, Pedro. Can you hear me?
Yes, perfect.
Okay, perfect. So, good morning, everyone. So I'm pleased to finish this morning of presentation. So part of the EOatSEE project, but we also take part in this ECFAS project. So I'm doing this presentation on behalf of all the team, which is quite a strong team. So we developed a proof of concept for implementing a coastal flood awareness system at European scale. This project was a research and innovation action funded by the European Commission, so through the Horizon 2020 framework. It was a 24-month project started in early January 2021, and so until the end of 2022. And we were 8 partners from 5 different countries, so merging research institutes with companies as well, working in the Copernicus field more generally. The main objective of the project was to contribute to an evolution of the Copernicus Emergency Service through an implementation of a system dedicated to the coastal flood awareness. So there is a system for the continental flood, but still missing one for the coastal flood issue and hazards. So that was really the purpose of this project, to develop this proof of concept. So we provided 5 days forecast of total water level, so something quite similar to what was presented this morning, but at pan-European scale and in real time. We provided also modeled flood extent and potential flood impact assessment, considering several different scenarios of total water level. And we also improved the mapping components, so using satellite images, first for the flood extent and impact assessment, but also for the observation of the shoreline displacement, so monitoring the erosion after a storm. We provided tool and algorithm for coastal storm risk assessment, and we also finished the project with a roadmap of implementation of the ECFAS system into the Copernicus Emergency Service, taking into account end-user requirement, needs, and also the international and European policies and legislation regarding this coastal flood risk management. So what did we do? So the conceptual framework of what we built is first to use Earth observation and non-Earth observation product and data sets as the one proposed by the different Copernicus service into 2 kind of components. The first one was a warning component based on modeling and forecast of total water level that were used to build a database of flood maps to estimate predict flooding, and also used to trigger such estimation of possible impact at the coast when the total water level was over some thresholds. So to provide a coastal flood assessment also on asset and population. So this is the warning part, and also to provide new mapping product for the impact and also for the shoreline displacement and the beach changes. So some detail now what we have developed. So for the hazard component, so it's a pan-European coverage. So we use operational forecast of total water levels, so coming from the Copernicus Marine Service, that provide time series of total water level that can be used for triggering coastal flood mapping based on identified thresholds. So we proposed 5 days forecast of hourly total water level, and this forecast was and were still are updated daily, so since April 2021. And the triggering threshold was computed by using a 1-year return period estimation, even if we estimated longer return period as well. The coastal flood awareness system and the impact assessment were done by using a flood model, which is already used for the continental flood estimation, which is the least flood FP model. So this model was calibrated and validated onto extreme event, real event, and build a database of test cases. Each event was characterized in terms of flood areas and quantity of water as well, and velocity of the water as well. the impact assessment method developed during the project was also verified and qualified. And we also use mapping product from satellite to do this validation. To prepare the catalog that I used to do the warning, so to estimate the flood impact over the coastal area, we established 20 different coastal regions, so considering 15 different flood scenarios. So at the end, we do estimation of flood over more than 500 coastal sectors, so leading to almost 8,000 flood maps and many impact layers during the estimation of the catalogs. So how does work the warning system? So over all the European coastline, we identify coastal points, so that's quite similarly to what we have done in EOatSEE as well. And the time series of total water level at each of these coastal points were monitored, and at each time they reach the threshold that was determined during the project, then the coastal sector was considered as potentially impacted, so what we call activated. And then regarding the situation, the selection of one scenario into the catalog is done, so that we can propose and estimate the potential flood extent and flooded impact to the potential impacted people and area. And we propose to evidence this possible impact through an aggregation of the coastal area impacted at an administrative layer, so what is the NUTS3 layer, that to provide onto a platform a warning system. Indeed, we built the final component of the ECFAS was the platform itself, so to provide online capability to see if there is a warning for your area at 5 days in advance. So you have an example here of the warning. So there is 5 different levels of warning, from dark green to red, and this is at NUTS level. And here you have another screenshot of the system that enabled user to see the total water level at each coastal point along the coastline. So you have here in example of yellow area that are warned, so activated, and you can click on one point and get the time series. So for the total water level with or without the wave impact, and when the threshold, which is the horizontal line here, is overpassed, then the warning is raised. So this platform was released at the end of the project in November 2022. It was kept available during last year for 2023, and it is now it has been stopped, but it will potentially be reopened. So it's still under discussion through the coastal hub of the Copernicus Marine Service. Besides this warning part, so the platform also gave access to mapping products. So these 2 examples of storm impact estimated through satellite images analysis, both the water extent and also the impacted area. And to finish, an example of shoreline estimation, which is also available on the platform, not automatically launched, but the results are available on the platform. So it's a semi-automatic shoreline position extraction, and this new tool enable people to do evaluation before and after storm of the impact and the potential reduction of the beach extension during this event. thank you very much for your attention. You can find some information on the website, which is still up, and also most of the results of the project were available and which are publicly available are on this Zenodo website. You can also have a look at. Thank you for your attention.
Okay, thanks very much, Claire. That was enlightening. And I think this is, we cannot wait until this is going to be available in Copernicus Emergency Service, because I think it's going to be very, very much appreciated in coastal areas. And let's hope that we can actually, at some point, evolve this for a global coverage, because right now I'm sure that people in Brazil would be benefiting from this kind of product. Well, maybe not right now, but a couple of weeks ago, that would be very convenient and useful, and actually, I would say, critical for preparing to this kind of problems and flooding. We have a immediate question for you already, Claire. So maybe you can answer directly. Can you see it in the chat, or should
I can see one about the sharing of the Zenodo link. So I will do it just after. One question.
The question then, I should probably read this, because we have also people in YouTube that are not seeing our chat.
Okay.
So we are getting a question regarding ECFA's total water level thresholds. If it's being based on local topographic features like dunes or seawall based, or if it is an exceedance value of this total water level. So if it's data driven.
Yes, thank you for the question, Pedro. Yes, it's a second solution. It's an exceedance value of total water level. So the threshold has been based on extreme value analysis as performed in the EOatSEE with some similar methodology, but we are not considering the local topography feature.
Okay, perfect. And indeed, there's one more practical maybe, which is asking who you are thinking about would be the main user, the end users of this product. If it's really the policymaker, the emergency responder, the insurance companies, what's your more interesting target?
During the project, the one of the most presented end user category was what you call the emergency responder, the civil protection.
Yep.
And there is clearly a need here to help in the action and in the prevention of the mean of intervention and preparation of the event.
Indeed, that's what I expected also. I think it's like the example I mentioned. If we had this in Brazil a couple weeks ago, for sure, my colleagues from civil defense there would be very happy and better equipped to deal with this storm. And about the scalability of this, Claire, there is a question if this is could it be produced in regions with less satellite coverage, like the Caribbean? Well, probably because it's over the equator and you have a longer revisit time. But
we discussed this point during the project, because during the final workshop, many needs were expressed to see if there is possibility to extend the system elsewhere. I think it's not a satellite coverage issue. It's much more the knowledge we have for the flood modeling. So the knowledge we have in terms of land cover, land use, and so technically speaking, it's reproducible everywhere, but still needs more or less effort to do it. But we could, I think, extend and apply this system everywhere, as we have a Copernicus Marine Service water level everywhere has a triggering part, And for the list flood and flood modeling, maybe requiring more effort from one place to another, but possible.
Indeed, it's for sure that if you can have this local calibration, this local data to improve these algorithms, it's going to be more accurate for sure.
Yeah,
but
sure. The more you have, the more accurate it is. Yeah.
Yeah, but indeed, the input data for the product is available globally already. You're not using anything that Copernicus only produced for Europe, like land use, land cover. It's also global from Copernicus.
There are some global data sets, but as for the calibration database, the more accurate you have, the more detailed information you have, the more accurate you will be in the forecast and the impact estimation. So for sure we may have higher resolution at the moment in Europe, but the quality you can target elsewhere has to be evaluated more precisely depending on the need and the data sets that are available there.
Indeed. Yeah, this was actually a very good presentation, I think, for closing our morning, because I think what you're saying now, Claire, it's connected to what we had in the previous presentations, because of course we have a more accurate global digital terrain model, more accurate global topography and bathymetry. For sure, it would facilitate the scalability of ECFAS or ECFAS-like solution to these other places also. We're getting these questions from Juliana Chavez from the Caribbean. So I'm not sure, Juliana, if you want to intervene. If you want, you can open we can open your mic and you can speak directly. But in the meantime, Juliana is asking about other disasters, hurricanes and storms. But I think in the end, flood is actually the impact that is resulting from different kinds of disasters.
Yes, so clearly ECFAS is dealing with storm surge impact, so hurricanes lead for sure to that, but the wind impact, for instance, during hurricanes are not taken into account into the system. We are just looking at the surge of total water level and the cost of ocean level at the cost, and not the wind impact.
But indeed, the wind is being taken account into the surge model, of course.
Yeah, into the ocean part, but not the wind direct impact onto the building, and so.
Yeah, indeed, more close to the coast. Okay, and we have one more question coming from Jérôme Benevist regarding what kind of in situ data we would need for the flood modeling. I think this current implementation in ECFAS, you're not really relying in situ data for operational, but maybe for the previous phase or calibration or validation. I'm not sure what sort of in situ data would be valuable in the process.
So I will not be able, I think, to answer myself on this. I will need to have the experts of the project close to me, but for sure we do not use in situ data. What we use for developing the flood model itself, what I know is that the soil nature is important, the urban area, the natural area, so all the land cover is important. So at the moment, and at the resolution, we did the estimation, so it was around 100 meter. The Copernicus databases were enough, but I'm not sure how much they use in situ data to validate. So sorry, Jérôme, I will have to answer you later.
Yeah, in the end, it's important to mention that, like I said before, this is a supply chain. That's why I thought that ECFAS would be nice to close the morning, because it's the last point of the supply chain, but actually everything that's coming before. So we opened this morning with the total water level. So we were discussing this, how to bring this total water level from altimetry data to closer to the coast, understanding the processes of water level transformation, wave transformation. And then we went for the topography and bathymetry, so talking about the vulnerability aspects, the morphology aspects, and of course, ECFAS put everything together with the flood modeling on top of this. So I guess in situ data can be used in different points on the supply chain, and the more the better for sure. But on the other hand, it also comes with the challenge of scalability. If we start integrating in situ data too much, your algorithm will become more locally calibrated, but maybe worse in terms of scalability. So there is some balance to be found in the middle there, probably.
Yeah, it's a question of scale, special scale you want to cover. So I think if you want to do something very local or more regional or on national level, maybe you cannot be so specific as well. So you have to be also homogeneous in the way you propose the information and you compute the information. So yeah, but for sure, this is a full chain, and the more information we can have somewhere can lead to a better estimation, and then a specific product or specific area.
Well, just to answer here in the chat, right now the attendees, they cannot talk directly. We have to give them their permission, so it's a bit bureaucratic. Maybe we can try to change this setting by the afternoon session. But thanks very much, Claire. I think this was a very good closing for the morning. We will have more engagement on the afternoon. I think more time to discuss, more time to address questions. At this time, of course, I'm urging you to answer this interactive live pool that I'm sharing. I'm sorry, I had some issues in the beginning because I was asking people to fulfill this, but without a way of changing the questions. So this is already a presentation of the results we have so far, but the QR code here can be used to access the pool. And as you can see, we have not many answers yet. We are starting to build here a word map, very interesting. And as expected, most of our participants today are coming from academia and from research. This makes sense because we are in a scientific roadmap workshop. But nevertheless, this pool will be kept open. There is already a lot of interesting results. This just came because I was not sharing correctly. So let's try to revisit this. I will show some updated results before the afternoon session. And as much as we progress during this day, as we keep progressing on the presentations, I'm actually starting to put here also some very specific questions on the products that are being presented. So this one is for already the total water level product. So we really welcome your contributions here. This is supposed to be as interactive as we can. We all know that it's very complicated and challenging to get interaction in online events, but I guess this is one of the best options we have by showing some results. And on the afternoon session, we will have much more time and we can actually discuss one by one these results that we're getting in the pool. Let me check if we still get let me see if we still got more questions. Of course, I also saw a request to send emails from the presenters, and of course, this is we are all welcome to exchange emails, but feel free also to contact directly the project to reach us in the webpage. There is a contact form there, and we shared in the beginning in the presentation, but of course in your invite for this workshop, you will also find the page where to connect with EOatSEE project directly, and then we can of course relay your questions to the specific person that is responsible for the presentations today, because of course some of those were external from the project, but we can easily access and relay these questions to them. So I will now actually pause our session for lunch. I think it was a long morning with a lot of information, a lot of food for thought, but now it's time to get some food for the body also. So let's have lunch, and we come back at, let me just confirm, 2:30 Central Time and 1:30 Western Time. So welcome back. We're going to start again. Not start again, but continue our workshop today. We've been discussing the different results that we got in EOatSEE project, and also other projects, all the novelty solutions that we have to cope with these coastal risks. We've been discussing this during the morning. Mostly focus on the long-range risk assessment. And now, during the afternoon, we will continue, and this time leaning a little bit more to the short-range temporal scale, so looking most about around predictability issues. And regarding that, we will start this afternoon session with a very interesting talk, which is a very good way to start because it encompasses a lot of different work. We're going to have welcome Mahid O'Donovan to talk about the Coast Predict initiative, which is a very interesting initiative which connected to the UN Ocean Decade. And in the end, it's kind of an umbrella for all sorts of different solutions and projects that we are developing on this topic. So once again, I remember you to access our live pool, which we'll be sharing the links in the chat. I will share it again. We are making good progress collecting some very interesting information, but this is ongoing during the session, so we'll be adding a couple more questions in the pool during this afternoon sessions so that we can review it all by the end of today's workshop. We'll have a more interactive discussion reviewing these answers that we got from the audience. So without further ado, Mahid, you have the floor. I can already see your screen, and welcome, and thanks very much to agree to participate in our workshop. And the floor is yours.
Okay, great. Thanks, Pedro. Hi, good afternoon, everybody. My name is Mairead O'Donovan, and I'm joining from Ireland to present, as Pedro mentioned, to present the Coast Predict programme. Coast Predict is a programme of the UN Decade of Ocean Science, and I'm leading the Secretariat, which is sponsored by CMCC. And I also want to just note the board and the chairs of the programme, so names that I'm sure some of you are familiar with. And the QR code will lead you to the website where you can get more information. So the Coast Predict programme aims to expand the global ocean observing system, and specifically to expand it into the coast. So the ambition is to co-design an integrated coastal ocean observing and predicting system, and for this to be done within a global framework with best practices and standards that could then be implemented locally to respond to local needs of communities and coastal managers and so on. So there's very much a focus on what the user needs are. Some of these are listed at the bottom, and some of them have particular relevance, of course, to sea level rise and extreme extreme sea level rise, so storm surge, climate impacts, information relevant to shipping and ports. And of course, there are others. And so for those of you who aren't familiar with the program, we have launched what we call Global Coast. So this is our framework for implementation. And we have been working on this for a while. We're still working on it. And what we're doing is we have established a global network of pilot sites. I'll talk a little bit more about that as well on the next slide. And so this would be the network, the global network, where we would demonstrate an integrated observing and forecasting system. And then we're also looking at the potential for a cloud-based infrastructure to provide a platform for sharing of knowledge, methodologies, sharing of data, and for this to make access to data and models more equitable, especially for countries in need of enhanced capacity. And the cloud-based infrastructure would also be used to develop for the shared development of services. And ultimately, there would be services delivered for risk assessment and management. So to initiate Global Coast, we launched a survey last year. So we ran it last summer for a couple of months. And we put a call out to the scientific community to get information about pilot sites in their regions. And we asked for them to define the issues and the stakeholders that would be of relevance to their pilot sites. And through the survey, we've started to build this network. So we had interest from over 120 pilot sites, 225 institutions in 65 countries. And we used the Robinson and Brink categorization of the global coastal ocean. So there were 32 regions of the global coastal ocean identified, and we asked people to note which region they fit within. So the colors on the map here represent the different regions. So you can see that we have a good global spread, albeit with very significant gaps, but it's a very good start to begin to establish this global network. And through the survey, we asked people to identify the priority impact areas for them. So we provided 9 impact areas that they could choose from, and they could choose up to 3. And on the next slide, what I've done is to kind of highlight some of the ones that are maybe most relevant to sea level rise and extreme sea level rise. So you can see that impact areas 1 and 2 were selected most frequently. So the first relates to I guess what this afternoon session is about in terms of early warning for real-time forecasting of extreme events. And then the impact area 2 related to more longer-term coastal climate downscaling and development of indicators of sea level and other impacts of climate change. And then impact area 4 was the other one that I wanted to highlight, just in relation to erosion and other short-term impacts on morphodynamics. I know there are other links, but I just thought it was worth kind of flagging those ones in particular. And the other thing we've done, just to illustrate what we kind of gathered through the survey that's of relevance to this group, is we just did quite a quick kind of course analysis of the pilot sites that specifically mentioned sea level rise. And there were 72 pilot sites that specifically noted it as a concern. So that included 44 nations. And of these, there was a particular focus on storm surge for 32 of the pilot sites. So you can see that it's a global issue. And what I want to do quickly here is just to show how through the survey, we wanted to, from the outset, ask pilot sites to identify who the users are. So there's a real focus on the solutions that are needed for users of the information, and we wanted to have that reflected from the initial survey. So these are the categories of stakeholder that were identified as being important end users, both upstream and downstream along the value chain. And these would be the sort of categories that we would need to consult in order to develop the solutions that will actually be fit for purpose and that will deliver the services that are needed locally. And so it's envisaged then that we will start at a number of pilot sites and develop and test systems at pilot sites, and then leverage the similarities between different regions, between different pilot sites, in order to accelerate what's happening in other regions and areas. And then this international collaboration will we hope help to accelerate the system development, and this will particularly support capacity development in countries where there's a particular need for enhancement of capacity, where there's current lack of resources. So at each pilot site, we will make use of existing available data from repositories. So that includes satellite and in situ data. And then there's also a need for new coastal in situ observations, especially what we think will be especially relevant here will be cost effective. So kind of low cost sensors and technologies and community sourced or citizen science. There's also a need for new remote sensing observations that will be relevant to the needs of the particular pilot sites and the local challenges. And then by gathering these will feed into transformative predictive models and into validation of the models, and ultimately will deliver information about coastal vulnerability and exposure data, which can be accessed through different levels of user interface and services. So this kind of brings me on to talking a bit more about the digital infrastructure that's envisaged at a global scale. So we are looking at examples of how computing, cloud-based computing infrastructure is being used to make science-based information accessible and usable. And what this would allow Global Coast to do is to increase the amount of coastal data that's open and freely available, particularly for countries in the global south where there is an existing shortage of data available. It would also provide access to a large volume of cost-efficient and community observations. And then also would provide access to tools and models, and would allow for shared service development and demonstration of services built on cloud data. So it would overall, within kind of the overall framework of Global Coast, it would remove the need for local HPC capacity, would provide more equitable access and knowledge sharing, and it would allow for accelerated services development. And all of these will be of particular importance to countries where there is limited capacity. So this is a schematic of what that digital infrastructure looks like. So a cloud-based platform that hosts the data from the coastal infrastructure, the longer decadal projections, other models, standards and best practices. And from this platform, we envisage that both private and public services could be built. And there are examples of some of the services, and also on the next slide, this is my last slide, just highlighting some of the services that would be perhaps particularly relevant to this group in terms of services that relate to sea level rise. And that's it from me. Thanks a lot. The QR again is for the website, to information there, and information about how to contact us. And of course, you can reach out to CMCC colleagues who are involved with EOatSEE for more information and to make the connection. So thanks a lot.
Thank you very much, Marie. I think that was quite interesting. I think maybe I missed, but I think I have a question regarding this. Basically, what's the timeline of the project? When you talked a lot about the things that are starting to happen and that are planned for the future. So are you still working during the whole decade? What is the timeline for the initiative?
Yeah, that's a good question. Yeah, so the Decade of Ocean Science is until 2030. We're a long way we're a long way into the decade now. We are, in the last year, we've made a lot of progress in terms of identifying the pilot sites. So we are hoping within the next year to begin actual implementation of pilot sites. And what that will involve is most likely identifying initial sites where we can start. And then the legacy of it would go beyond the decade in terms of what it would contribute to the global ocean observing system. So the program as such is kind of the demonstration, the development of the science and the demonstration of something that could ultimately become a global coastal ocean observing system or systems.
But the idea is here, so again, I have to insist because I'm thinking about the practical applications, and you use the word demonstration. So the idea is that this becomes a pool of demonstrations, and people can learn and develop their systems, or is it to actually transition into an operational service or something that is actually to be provided to society?
Yeah. No, it would be to demonstrate, and through the cloud-based infrastructure to allow for, I mean, that's kind of part of the transformative part of the concept, because that provides the platform for the sharing and for those demonstration sites to actually become operational, and for the learnings, the best practices to be shared and implemented at other sites. So we have a number of projects and pilot sites, for example, that have a geographical focus in terms of developing national or regional coastal observing systems. And for example, the Mediterranean, what's happening with the Mediterranean, which CMCC and I'm sure other organizations here are quite involved in, provides a good model for how that might be implemented in other places operationally.
Perfect. Okay, thanks very much, Mahid. I think that's all from me, and I don't see any other question in the chat. But again, thanks. This was an excellent opening for this afternoon session. And if we get other questions, I will make sure to forward them to you offline.
Okay,
we can discuss. Thanks again. Okay, so we'll now transition to our next presentation, which will talk about the storm surge and flood modeling during an extreme sea level event. And this is going to be presented by one of our colleagues from EOatSEE, this is Lorenzo Mentaschi from the University of Bologna. So go ahead, Lorenzo, the floor is yours.
Okay, thank you. So I'll share my screen. You can see my screen in full screen?
Yes, we see
okay.
area.
Okay. So I'll speak about the Adriatic Sea, this area on which we worked from Unibo together with the colleagues from CMCC. Let's see if I manage to change slide. Yes. Okay, so one thing that was done on this area, the water levels were investigated in the short term using a model, an unstructured model covering the whole Adriatic Sea with a resolution of 2.5 kilometers offshore up to 300, 100 meters near shore, so quite high resolution. Able to estimate also the coupling near shore between currents and water levels and waves. And this domain was used to run a couple model of Scheifen for circulation and water levels, and WaveWatch 3 for waves. And by the way, now this model is also operational with this ADRI-FS, ADRI forecast system. And this model, which I repeat is dedicated to the so-called short-term approach of the EOatSEE project, was run for 3 years, from 2018 to 2021. That is 4 years, sorry. And in this period was extensively compared with Xtrack, in particular the Sentinel-3 extract. And this with a special focus on 3 areas, on 3 locations, which are Otranto, which is close to the map, let's say, of the Adriatic Sea, Ancona and Ravenna, because in these 3 locations we also have tidal gauges to compare with. And now you can see from this figure that the comparison with the tidal gauge is quite good. Here we have the blue line is the tidal gauge, the red line is the model results. And the task was to compare this with also extract, and also we compared in this activity, which was led by CMCC, there was also a comparison of extract with the tidal gauge. And in particular, by aggregating the extract of sea level anomaly by month and comparing the result with the model, we find in general a very good result, as you can see from this this comparison here. The dots are the extract from Sentinel-3, and the black dot, the red dots are the model, and the black dots are the tidal gauge, the results from the tidal gauge. And this is essentially the same comparison done with the scatter plot. Here you can see the comparison between the sea level anomaly from the tidal gauge and the extract, and you can see that they closely align in a scatter plot. And this is the same comparing the extract with the model. And an interesting thing that you can see is that in 2 locations on 3, there is a better fit between the model and extract than between extract and the tidal gauge, which is quite interesting. And here you can see the comparison in terms of time series, both with the tidal gauge and with the extract. Now let us talk about the second part of our investigation of the Adriatic area, which was in particular about flood modeling. Flood modeling was carried out using the LISLAD FP model, that is the same that has been used in the ECFAS project. In particular, we set up a domain covering the whole Emilia-Romagna coast with a resolution of 50 meters, and the Puglia coast with a resolution of 30 meters, using special local, let's say, digital elevation models developed based on LiDAR from the Regione Emilia-Romagna and the University of Bari. As a forcing, we used modeling data from a hindcast that we developed in 2023, a global hindcast with a quite high resolution of 2-4 kilometers along the coast. Recently, we also used data from EOatSEE, for which we'll show the results now for the first time, even if today is the scientific roadmap. I think is worth showing a slide about this. While for Puglia, we used modeling data from CMCC. And we did also some experiments using the precipitation data from EOPS to modeling some compound effect. So to start, for the Puglia region, we ran the only case that we know about which we have a flood map, which was an event in 2019. And essentially, not all the domain was covered by an observational flood map, but even in the locations where we don't have an observational flood map, like in the location called Hippocampor and in the location called Salina, we know from kind of media that these areas were indeed flooded. While in the area where there is an observational flood map, we have quite a good fit with the observational flood map. This may be not very clear from here, but here it will be more clear, because this blue line represents the let's say, the boundary of the flooded area according to the observational flood map, while the colored area is the area that has been flooded by our model. So you can see that in this specific case, the fit is very good. About the case in Emilia-Romagna, we have two cases that we model. We modeled the case of 2015, which resulted in a major flood in a large part of the coast of Emilia-Romagna, and a smaller event in 2022. And we can see that for the event of 2015, we were able, since already, let's say, more than 1 year, to do a rather good job in modeling the flood map, specifically in this figure that covers just a part of the domain. We can see the black line. The black line represents the observational flood map, while the colored area represents the area inundated by our model. And also this figure here shows the impact of precipitations that we added with EOPS. I recall that EOPS is a rather coarse data set, so the two informations have a different degree of uncertainty, and that's why it is useful to show the results both without the precipitation and with the precipitations. But you can see that for the 2015 event, the precipitation had some degree of risk, let's say. For the event of 2022, we found that the setup that used to model correctly the event of 2015, the same setup tends to grossly overestimate the flooded area in Emilia-Romagna. Why? Because the fact is that during the winter in Emilia-Romagna, they erect this kind of artificial dune that is there only during the winter, and then during the summer they dismantle it. I think they dismantled it, let's say, less than 1 month ago. And in 2015, we had this big flood because there was a quite powerful wave that managed to erode completely this protection in some areas, and this caused this major flood. Instead, in 2022, this managed to protect effectively the coast from the inundation, and that's why the observational flood map in 2022 is much smaller than in 2015. But in our setup that we used 1 year ago, this was not reproduced. So what we did, we added in the model ListFloodFP a parameterization of a kind of temporary dune protection and its failure. So essentially, here we set a failure water depth, and when this water depth is reached, essentially we model a dune failure and we let the flood propagate. And we can see that if we introduce this kind of protection with the very same setup, we manage to reproduce correctly both the event of 2015. You can see here the event with dune. Essentially, the flooded area is the same because there is a failure of the dunes. While in 2022, we can see that we can reproduce the fact that the dune did not fail, and so the flood map reproduced by the model is very teeny and similar to the observational flood map. Whereas if we don't put these protections, we see that we overflood a lot in this event. Something that I would repeat is that, and that I show here for the first time in the whole project, is that now that we have a model setup that we think is reliable, we also forced it using the total water level from EOatSEE, the same that we showed together with Pedro in the first presentation. And we can see that the flood map reproduced for the event of 2015 is qualitatively very similar to the one reproduced using modeling data. The difference is that we have somehow more flood and a bit deeper water levels, but on the whole they are very much in agreement, and this I think is a good showcase of possible predictability of the event based on the data produced in the EOatSEE project. The last thing that I would like to show you is this ongoing work of AI-based prediction of storm surge. This model, this AI-based model was developed based on dynamic modeling results. In particular, we carried out long-term high-resolution simulations of the storm surge in the Northern Adriatic using this domain, which has a resolution of 3 kilometers offshore and 50 meters near shore, so very high resolution. And we set it up using quite good wind data, in particular a downscaling with the resolution of 3 kilometers, so able also to reproduce the small scale dynamics that are important in this area. And then this model was used to train AI model. In particular, we compare different methodology. Here we show only a multilinear regression and the more sophisticated long short-term memory approach. And we can see that in this work, we obtain quite a good result using the LSTM. And in particular, we see that the system is not completely linear, so that the LSTM does in general a better job than the multilinear in reproducing especially the extremes. And finally, something that I would mention is that this activity is thought to be very oriented towards research, and indeed are in production several scientific papers. In particular, one that has been submitted now about this last modeling activity, and also the activity about coastal flood modeling is going to be submitted soon. And also essentially the other activity that I showed here are going to be topics of scientific papers. And that's all from my side.
Okay, thanks very much, Lorenzo. This is very interesting. Lorenzo has been responsible for some of the most innovative initiatives that we had in EOatSEE, really pushing the envelope here on how much we can try to do. And I think it's really interesting, especially your adjustments of the model, providing that that algorithm to represent the small dune, that is man-made dune. I think that's very smart solution, and that's the kind of solution that probably we will need to scale up this kind of approach, because I'm pretty sure that every little stretch of the coast will have always deserve some minor adaptation in the algorithm. So that's some food for thought, because we need to comply with that. We need to allow for this kind of adjustments in our future solution, because especially with these man-made structures, this is for sure something that we always will have to put some special input in these locally calibrated models. And of course, the AI downscale points out the future transition to a more data-driven kind of modeling and not so much physics-based. So really interesting work, and I recommend everyone to wait patiently for these publications, because I think you're going to have a lot of interesting insights on them.
Okay, thanks for the kind words.
Lorenzo, I also don't have any questions right now on the chat, so similar to the others, we will make sure to convene. This workshop has this kind of not only simultaneous nature, because we have also the recording on YouTube, where it's exposed to this large community that Air Center can bring. So we might come with new questions after the session, and then we, of course, will address them offline and try to enrich this discussion. So now let's transition for our next presenter, which is also an Italian. So we're gonna welcome Salvatore Causio. We will be presenting two different use cases that were developed here in EOatSEE, where we are trying to benchmark these EO-based solutions to short-term predictability. So, of course, we are talking about combining this with results from numerical models. Some of those were already set up before our project. Others are being evolved. Others are just recently being implemented. So it's going to be a bit of a showcase of what we can do in terms of numerical modeling with this data. And just before you start, Salvatore, I once again make the remark that if you have not yet complete our live pool, it's still ongoing. And like I said, we are still adding a couple questions during these presentations as the results are presented. And we are going to get together at 6 Central Time, not 6, no, at 4:16 Central Time to have some discussion on those feedback that we are getting from the community. And without further ado, please go ahead, Salvatore, and the floor is yours. Thanks.
Okay, thanks, Pedro. So, good evening, everyone. I'm Salvatore from CMCC, and during this presentation, I will go through work that we did in assessment wave current interaction during some extreme events. To do that, we investigate different extreme events in different parts of the world. The first extreme event we investigate was the Medicaid Janos, which impacted the Mediterranean Sea in 2020. So Medicaid means exactly Mediterranean hurricanes, which are similar to tropical storm develops outside. They are called extratropical, storm. And this we focused on Medicaid for this Medicaid for two reasons. One is because it's the strongest storm we recorded, so since 1969. But was important for us from modeling point of view because this Medicaid landed close in Greece, close to a tide gauge. So for our purposes, it was really interesting this because we have the measurement there, even by not only, from satellite, but even for a tide gauge. This is our modeling framework. As already anticipated, Lorenzo, we have this coupled system, which is made of WaveWatch, which is a wave model, is a third generation wave model, which solve action density balance equation, and which is online coupled with a two-way interaction. Is able to, thanks to a peculiar framework, numerical framework, is able to exchange online two ways interaction between a circulation model. The circulation model we adopted is Scheibe, which is a three-dimensional fully baroclinic hydrodynamic model. And what is important for us is that both of these model works with or solve equation on a triangular base grid. This means that we are able to increase the resolution where we are interested. In general, we focus on the cost. For this case, for instance, we will have in this area 2 kilometers of resolution offshore and 50 meters of resolution along the coastline. In the last, I can set up the pointer, laser pointer. Okay, yeah. In the last panel, we have a bit of, description of what we are going to address. So with this study, we would like to characterize the wave setup during this event. So the contribution to the from the waves to the total water level. Before going to the sea level, we will have a look to the validation of waves close to, I don't know if I have the cycle, no, need to move this one, but I cannot move the picture here. Okay. So this is the Medicane, which is traveling the central Mediterranean Sea, is approaching towards the Greece, where we have here the tide gauge, but we have also wave mooring, which provide us data for the validation. And in both cases, both considering the mooring, the wave mooring, or in case of 3 different satellites, which were able to record the Medicane, our model has been calibrated. And it provides very nice, very good quality. I mean, with a very high correlation. From 92 is the worst with Altica, and 96 for JSON 3. Concerning the sea level, this is the most important part of this this investigation. Here we can have the snapshot in the moment in which the Janos is approaching to coast, and this is the Greece coastline. So we have Kefalonia, Zakynthos, and Patras Gulf, and exactly in this position here we have the tide gauge. And in this tide gauge provide us, of course, some data which are represented here from the red dashed line. And we compare to assess the contribution of waves to the total sea level. We compare 2 different simulations, one in which the circulation model was coupled with the wave model, and is represented by the green line here in the time series. And then we included this interaction, and we obtained, this is what we obtained. So with the black solid line, as you can appreciate during the peak of the event, which is here highlighted and with the shaded yellow, it's much better. So we improved a lot, and this is too important to stress how the wave contribution it's important even in this case. I mean, to define the correct total water level. The next study, the next investigation that we have was in another part of the world. We are in the Indian Ocean now, and we are going to address a much stronger event, which is the Cyclone Freddy, which occurred in 2023, so in February. But what is important to say is that while in the first presentation we observed the effect of waves on currents, now we are going to do the opposite. So we use this case to assess the role of currents on waves. Cyclone Freddy developed in northwestern Australia, then traveled quite soon, reached a very high intensity from 3, 4, even 5, was peaking with 270 kilometer per hour. And on 21 of February, it landed close to the Mananjari city here in Madagascar. Again, the modeling approach we adopt is almost the same as what we've seen before. So the Scheiffen model for the hydrodynamics, and the wave watch for wave. Here again, it's supported by ERA 5, almost the same approach. But before going to assess the effect of currents on the waves, what we would like to show is that we did some attribution test according to the total water level for the event. And what we observed, it's here represented in red, the total water level during the event close to the Mananjari city, is that very likely the surge of the event, which is represented in blue, was not in phase with the tides. This means that just by chance, I mean, we don't have during this event 40 centimeter higher waves. So this means that the cyclone Freddy has been so strong, so deadly event, but it could be just by chance, just by phasing. I mean, when putting in phase surge and the tides, it could be even more dangerous. So reaching 2 meters, for instance, instead of 1.6 meter. Let's come back to our topic, which was the effect of the currents and on waves. We selected these events even because in the northern part of the Madagascar, there is this south equatorial current, which is driven by trade wind. When approach the northern part of Madagascar, this south equatorial current is split in two different currents. One is going up, so in the northern part, the other one is going towards the south, it creating an East Madagascar current. These two branches are our interest during this study. And this East Madagascar current then will converge together with the Mozambique current into one of the most important current of the world, which is the Agulhas current. To do this work, so to study the impact of this current on the waves, what we did here is to have two simulations. One is let's say only taking consideration the wind for the waves, and the other case, which is highlighted in blue, we will call a VCF, which means that the wave model is taking consideration not only wind but even the currents. And in this plot here, we have a bit some example, I mean some plot of the event. In the first panel and the left, we have the significant wave height. This is exactly in February to 2022, February 2023, and this is the event when is forced both. It's considering both current and wind. On the rightmost panel, we have the circulation induced. I mean, the normal circulation at the beginning, while when the event, so the cyclone is approaching, of course, this circulation will change. And into the middle, in the middle panel, we have the difference that we have in significant wave height if we consider or not the currents. As you can see, at the end, we have a very strong difference in the southern part. But let's go step by step. This is the normal case. As you can appreciate in the northern part and the southern part, of course, towards this promontory here, the East Madagascar current is in some way reducing the significant wave height along the coast for the Madagascar. This is the snapshot when the cyclone is almost in the middle of the domain, and the effect of this current north and south is intensified for the northern part. It's in some way disappear here, the effect in the middle. But then after, this is exactly after the cyclone passed on land, so it's moving towards the Mozambique channel. We have a very strong effect of this intensified current in the southern part. So this is extremely reducing the significant wave height along the coast in the southern part of the Madagascar. And during this, so in this plots, we will see in 2 time series the evolution of the maximum wave height during this event. As you can appreciate, the red it's always larger. It's close to a bit less than 1 meter, larger than the blue, which this means that the effect of currents on the waves as on the maximum significant wave height. During this event is comparable to at least 1 meter, while in the map here in the left, we can appreciate the evolution of the max, so the location of the maximum values. And as you can see, after the cyclone approach to the coast and moves on land, the maximum is separated. So this is the effect of the current, which moves offshore the highest waves. So what we would like to say is that this event has been really dangerous and really harmful, but it could be even in some cases, even by chance, as we've seen from the total water level, it could be potentially more dangerous than what we observed. And even the displacement here, or the maximum significant wave maximum, could be, I mean, an important point to address, even in case of forecasting, because in this case here we appreciate that we can have a very different solution if we not consider in, for instance, forecasting system this effect. So what we did in this part of this of the project of EOatSEE is the investigation of wave current interaction during different extreme events. And we did this by an event-based approach. So we investigated the Medigain in 2020, Medigain Llanos, or the Freddy cyclone in the Indian Ocean. And we concluded, I mean, with this investigation, that it would be very important to include this process even in case of forecasting system. This work will be, I mean, separated into different publications. So we are working on 2 different publication proposals. One is related to a general assessment of a general global coastal ocean model for assessing extreme events. And we will have in this presentation both the study we already seen about the Freddy cyclone, and the next we are going to see for the Azure. And the last publication, the second one, should be only related to the wave setup and the wave contribution to the sea level during the Medigain event in the Mediterranean Sea. And I concluded at least this part of the work.
Thanks, Salvatore. This is quite interesting, demonstrating just how far these interactions go. I'm sorry, I had my camera off. Indeed, I think we could transition directly to the next presentation. I still don't have any specific questions for you. But for sure we will make sure to answer any other questions that come during the presentation. So feel free, anyone, to make your questions in the chat. Also for those watching in YouTube, the same, you can make the questions in the chat and we can just relay them here to the presenters. And feel free to make questions also regarding the previous presentations, because we have also the people here still on the call, and we can try to answer those immediately. And yeah, go for the Salvatore. You can go on and talk a bit about the Azores now.
Okay, thanks again for the floor. This let's say third case is related to another event, and with a bit more different objective. In this case, we try to focus on increasing the capability for predictive waves and following the storm in a certain way. The extreme event we are going to present here, we are going to see, is the Hurricane Lorenzo, which again is a very strong hurricane, again with the category 5, and this is one of the most dangerous, strongest hurricane in the Atlantic Ocean. The hurricane Lorenzo, of course, starts close to the equator, then move towards north, peaking again 260 kilometers per hour as wind. But fortunately, the wind speed drops when hit the Azore Island. In particular, two different islands has been touched by this, by Corvo and Flores Island. And again, I'm trying to, okay, here. And I mean, this is one of the strongest, as I anticipate. No, it's the strongest since 1851. And when the Azore was just only, let's say, only category 2 hurricane, even if just a bit southern, I mean, was category 5 hurricane. We already know a bit very well our numerical setup, so Scheiffen and wave watch. They are always the same model. But before going to the waves, again, I would like just to give you a bit of information about the sea level. In this case, here we have a Corvo and Flores, what is the two most heated island by the hurricane. And in the northern plot, we have a plot from Scheiffen, from our simulation, while we have in the bottom panel the global product of our CMEMS. Unfortunately, we don't have a very high resolution in time observation to compare the data, but what we observed, just picking up in few points in 3 different islands, the sea level, what we observed is that while in the farthest island, our sea level was very comparable to the one from the global product from CMEMS. If you consider the P1, P2, so Corvo and Flores Island, which was intensively affected by the hurricane, our model was much more sensitive. And this is, of course, related to high resolution physics related to more coastal approaches. So this is, again, an important point we addressed, but we are going to address a bit, to validate a bit more these results. But the main topic of this study was mainly related to the waves. So starting from a work Lorenzo did last year, we developed and we implemented a global model related to all the coast of the world. And this helped us to have a global application, of course, but with focus on cost, which help, at least in the case of the hurricane, to track the full events. And this is important because when the hurricane is far from our domain, it is just receiving, if the swell is directed towards our domain, I mean, it's just receiving swell, not directly the wind. And because during the nesting, we have to, if we don't have the spectrum for the boundary of our nested domain, we have to rebuild it, which is, an approximated solution of the spectrum. We could have not so good, let's take the pictures, not so good results, at least when the hurricane is far from our domain. For this reason, we decided to get this implementation global, which was able to track the whole events and for sure avoid this complicated downscaling for certain condition. And on the other side, we have also a two-way interaction between the scale in this way. What I mean is that if we have a direct normal downscaling, we will just receiving the external environment within our domain. But in this case, we are also able to propagate outside for large-scale phenomena the wave action in this case. It is just very briefly a few details about this implementation, which is 50 kilometers offshore, 2 kilometers close the island, and is forced by ERA 5. We focus our attention on the validation in this case. In fact, we used more than 300 buoys all over the world, a lot of data from satellite. And here in the leftmost panel, so we have the validation towards moorings, which are, of course, mainly related to cost. I mean, they're much close to the cost. And our results state that we have almost 90% of error all over the world, with a slight, let's say, negative bias, which is normal for this type of model. When we validated the full ocean, we have much better results. We state, I mean, we had close to 13% of normalized root mean square error, which is pretty good for this application. And here a validation dedicated to the event. So here the Hurricane Lorenzo is developed, now starting to intensify, and then it bend towards the Azore Island. So in this red box, we have the track we used to validate the event for the calibration even. And if you had a look to the scatter plot, we are very proud, I mean, of these results, because the model was able to have a correlation around 0.97, so 97%. And we have a slope which is around 1.0, so an almost perfect slope. And this is important result because in general, what we observe with this model is that we have an underestimation of the extreme, while in this case has been perfectly fitted. So it's a very, very important result to having such tool for dedicated to extreme events. And again, so what we've seen is another event-based approach. So towards assessing this, in this case, the capability to predict waves, but for extreme. Our important results in this case was this the development of this global coastal ocean model for waves, which both as anticipated as this dynamical downscaling from large scale towards the coast, but then allows to this mutual exchange between the small scale towards the large scale. And again, another important point is that if we use such model as forecasting tool, this doesn't need any relocation or development if you need soon, for instance, to map an event which is forming somewhere, because of course it has this global distribution, so it's always ready to have simulation all over in all the places of the world. As anticipated before, this work will be part of the publication together with the Freddy cyclone for the Madagascar in developing and assessing this global coastal ocean modeling for extreme events. And I'm at the end, so I concluded also this presentation.
Hey, thanks very much, Salvatore. That's also another interesting, different application, different aspect to be highlighted. So really interesting to show this to the community. Let's transition directly to our next presentation, which is to be actually the last of today's before we engage in a discussion. And for that, I will call Lorenzo once again to present us another related initiative, the initiative that is pretty much related to this topic, which is the AdriaClean and AdriaClean Plus projects. It's the projects that are implemented this operational model for forecast in the Adriatic. Lorenzo, I am not sure you are still hearing me. Yeah, here he is.
Yes. Just
I guess Salvatore ended a little bit earlier than the schedule, so we are 5 minutes ahead of the schedules now. But that's good. So take your time. You can actually use a little bit more time to present if you want.
Wait a second. So I share my screen. Okay, so now you see my screen in full screen mode.
Yes, that's working, Lorenzo. Thanks.
Okay, so let us these closely related projects, AdriaClean and AdriaClean Plus. These are two Interreg projects, Italy-Croatia, where Interreg is a kind of European project, but a bit different from the ones like Horizon Europe, because it is managed by the European Regional Development Fund and managed by DG Regio. And essentially, this is a kind of Interreg that is dedicated to the territories of the Italy and Croatia that neighbors the Adriatic Sea. And this indeed the fact that I'm based in Ravenna give the University of Bologna the possibility to participating in this kind of projects. So the first of the two projects is the AdriaClean. AdriaClean is essentially it is a project that already ended not long ago in June 2023. And it was dedicated to essentially study the impact of climate changes in the region of the Adriatic Sea. And the objective of the project was to study the impact of the, as I said, of the climate changes on the Adriatic Sea, but at high resolution, let's say, because the rationale behind this kind of project is that we have a lot of projections, we have a CMIP initiative, we have the Cordex initiative. However, these are very coarse. The resolutions that you have in the CMIP is in the order of 1 degree. The resolution that you have in Cordex is maximum like in around 10 kilometers. And this is a bit too coarse to do a good job in a small basin like the Adriatic Sea, where the mesoscale dynamic is important. And so the idea was, let us take this information that we have, let we take MedCordex models that are at high resolution, and let us downscale them using a modeling chain. And let us see what is the result in the scale of the Adriatic Sea. And in this sense, it is quite an innovative approach, because in general, you see that the number of ensemble members is prioritized with respect to the resolution of the modeling chain. So the main objective was essentially a modeling endeavor, and I must say I'm more a modeling person, so I was more involved in this part of the work. But there was also an important component regarding the improvement of the observational network of coastal phenomena in the at Adriatic scale. The limitation of this project is that there is no mention of the remote sensing of satellite data, essentially. The focus of the project was on the whole Adriatic Sea. So this modeling chain that we developed covered the whole Adriatic Sea, but also we go to very high resolution at the given is the equivalent of the EOatSEE focus area. Here we call them pilot areas. We call them pilot areas, and essentially they correspond to the cost of the different regions of the territories that are involved in the project. And in essence, the modeling chain that we developed is quite complex and quite comprehensive. As you can see, we have an atmospheric model. So we take the MetCordex data and we downscale them down to a resolution of 6 kilometers from, if I'm correct, 25 kilometers of the MetCordex. And also this WRF model that we developed has several levels, has 60 levels, and also has a land surface submodel. This atmospheric model is used in turn to force a hydrological model that was used to model the catchment areas. And here there will be a dedicated slide. It was quite an important job that was done by the colleagues of CMCC using WRF Hydro to reproduce with the resolution of, if I'm correct, 500 meters, basically all the catchments of the Adriatic Sea. Then this data, the atmosphere and the hydrology, was used as a boundary condition for an ocean model. In particular, the NEMO model was used with a resolution on Adriatic at Adriatic scale of 2 kilometers and 120 levels. And in turn, this circulation model was used to force, essentially the output of the circulation model, but more than that, also the atmospheric model was used as a forcing for a wave model, which also had a resolution of 2 kilometers, and also for a biogeochemical model that was run on the same grid that was used for the circulation model. So you can see a quite comprehensive modeling chain. And more than that, for several of the focus areas, for example, here you can see it for the Veneto coast, also local downscaling at a very high resolution were developed. And here I show the mesh that was developed for the Veneto coast, but the same work was done on the Emilia-Romagna coast, for example, and we have a paper that we are preparing in this respect. And then, besides the modeling effort, as we know, a very important aspect of this kind of project is then translating the information that we can get from the models, but also from the observations, into something that can be used by the so-called stakeholders. So this was meant to be a project that can help the local authorities and the coastal managers to produce adaptation plans. And to be able to be used by the stakeholders, this kind of information need to be translated into so-called indicators that they can understand easily. And we developed, and sometimes when we run models, we neglect this aspect of the work, but in reality, for us, it took a lot of time to conceive and develop these indicators that could be used, that are supposed to be easier to interpret and that can be used by the stakeholders. And we can see we developed a high quantity of them. We developed indicators about the water resources, about drought, about marine ecosystem, about coastal hazard, and so on. Simply the development of all this and conceptualization of all this indicator took itself some time. Here there is a diagram of the model that was developed. In particular, there is also this representation of the MED-Cordex, because the MED-Cordex itself is a downscaling of a CMIP5 global climate model. And essentially, the MED-Cordex that we used had a resolution of 30 kilometers. I saw the 25 kilometers. Instead, it is 30 kilometers and time step of 3 hours. And also, in the end, we only worked on a single model because it was the only one that had all the data necessary for our downscaling. And this, I'll talk later about this, but this is also somehow a limitation of this project, because in the end, for a climate project, we use just one model, which is, in general, you speak about ensembles when you speak about climate changes. However, it was a constraint that was dictated by the fact that it was the only model with all the data that were necessary to run our modeling chain. And then these data were used, as I said, to force our WRF model, which had a resolution of 6 kilometers, which is the minimum that you can get from let's say, nesting from a model with a resolution of 30 kilometers, and had many more levels than that. And also, I forgot to mention that the simulations that we performed were carried out under the representative concentration pathway scenario 8.5, which is the most extreme, but only from 1990 to 2050. These data were used in turn to force our hydrological model, which had a resolution, as I said, of 600 meters, and for a soil represented with 4 layers. And then this in turn was used to force the model, which was a bit at the center of the project, which is the NEMO model with a resolution of 2 kilometers. And here you can see a bit the quite impressive work done by the colleagues of the CMCC in reproducing essentially all the catchment area that you can think about in the Adriatic Sea. And essentially in this, 145 catchment areas were identified and modeled with WRF hydro. And then out of this, only 71 were used because the others were very small and so relatively ininfluent. And also, essentially, it was not really possible to validate the results. Instead, for the 71 that were used, all the data were also the data were validated versus station data. And I would also mention that 71 catchments is anyway much more than the catchments that are currently used in the Copernicus operational. And also in the Copernicus operational, they don't have a dedicated model that models the catchments. They simply use either climatologies of river runoff, or they use the recent station data. So the fact that in this project we reproduced in a way so detailed the dynamic of the river is for sure an important innovation. And indeed, there are scientific papers that came out of this, in particular, a couple of them that were recently accepted on Frontiers of Climate. And the results of the circulation model were used to assess the impact of the ongoing climate changes in several ways. And in particular, here you can see the results with regard to an important topic, which is the one of the marine heat waves, which are an event that can have a big impact on the ecosystems. And this is still under investigation, the impact of the marine heat waves on the ecosystem. But from the analysis that we did on our model, we can see that at least according to our projections, there is going to be a consistent increase in the both the number and the duration of the marine heat waves. In particular, in the first two histogram, you can see the duration of the marine heat waves in the, let's say, the so-called baseline period, that is the present, and the number of marine heat waves in the present, while these red histograms are the same information for the projected future from 2030 to 2050. So the last 20 years of our modeling endeavor. And in general, to describe the impact of climate change on the environment based on the results of the circulation model, there is also here a paper that is in preparation and will be submitted soon in Frontiers of Climate. By the way, also for this project, we had a special issue dedicated to the project in this journal. And our particular contribution in the modeling side in this project was biogeochemical modeling from UNIBO, where we set up a quite comprehensive biogeochemical model based on the model BFM, which provide a quite accurate description of both offshore and nearshore dynamics. And these were extensively validated versus observations in the so-called baseline period, so in the period in the past between 1990 and 2010. And the fact that the results, the ability, this model has a good ability to reproduce the biogeochemical processes of the Adriatic Sea is also confirmed by the fact that if we use this for an AI characterization of the Adriatic ecoregions, AI, I mean, based on artificial intelligence, we get a reasonable clustering of the ecoregions of the Adriatic Sea. In particular, you can see this area on the northwest, which is characterized by a quite estuarine ecosystem and nutrient-rich and very often eutrophic ecosystem. Other coastal areas that are this one in southern Italy, and this is in the eastern coast of the Adriatic Sea, which are also coastal but are a bit less nutrient-rich than the northern estuarine. And then other three areas that are more characterized by oligotrophic conditions. And this one in the south is also characterized by quite deep waters. In particular, here the Adriatic Sea is a bit more quote-unquote abyssal than the rest, because it can reach up to 1,300, if I recall correctly, depth, while in the north, generally the other parts of the Adriatic Sea are quite shallow. And the results from this biogeochemical model points towards this direction. Essentially, there is a deoxygenation of the Adriatic Sea, which is consistent with the increase in temperature, which reduces the solubility of the oxygen. There is an increase in temperature and increase in salinity, and both lead to a decrease in solubility of the oxygen. There is a tendency in acidification, which is more pronounced in deep areas than in estuarine coastal areas, because the chemicals that are carried by the rivers tend to buffer a bit the acidification. So we can see that the acidification is going to be a bit stronger in the deep areas. This is the southern deep, and less so in the estuarine areas. There is, we project in our model a strong decrease in primary production and chlorophyll concentration, especially in the estuarine coastal areas. And this is related with the fact that in our model, in our projections, we find a very significant decrease in river runoff projected for the next 30 years in the Po River, which is about year on year is about 35%. So it is very strong, and this has a huge impact on the ecosystems of the northeast. While we have also a decrease in river discharge also in other areas, but in the other areas, the river dynamics is a bit less important. And here I need to say that, yes, we see this strong tendency towards oligotrophication, but oligotrophication in the Adriatic Sea is something that is observed essentially since the 2000s. So is a well-known tendency. Here we just point towards an acceleration of this project. And these results were also recently published in a paper, still in Frontiers in Climate, which is this journal where we had this, we still have this special edition on adaptation and planning in the Adriatic Sea. And now I talked about this project that, as I said, closed recently. And now we have let's say a continuation of this project, because we know that our project Adriaclim was very successful, but we know that there were limitations. As we must say, you always find limitations when you do scientific work, and you know that there are things that you would like to do more. So we applied for another interreg, and we got it. So this started right now. We had the kickoff meeting 1 month ago. And so essentially, why did we find that we had the limitation in our previous project? Because first of all, due to the high computational cost, and to the fact that indeed the limitations are both, so the costs are both computational and of storage. Computational cost means that running one of these models with this modeling change is extremely costly from a point of view of the required resources. And also because always when you run a model, you find that there is some problem and you have to run it, rerun again. So we ran it many times, and this was a very high computational cost. Problems in storage, because a lot of institutes don't save all the information that are needed. And so essentially we found only one model that was viable to drive our modeling change of Adriaclim. This means that we cannot really assess the uncertainty of our projections. So for example, in the work on biogeochemistry or on heat wave, we find that there is a decrease in primary production, for example, in the estuarine areas. But this has a validity as a what-if scenario. We cannot really assess the uncertainty in this information, even from a point of view of the climate study, because we don't have other ensemble members, say. And also, there are some processes that are important that were somehow neglected, like the salinity at the river mouth. And essentially, so our modeling chain give a lot of information and let also infer informations, for example, about the salinity at the river mouths, but essentially you cannot really estimate from the model themselves these phenomena. While these things, we think it would be nice to add them in the modeling chain. And out of these limitations that we found in the ADRACLIM project came out this new project, which is ADRACLIM Plus, which essentially has the same kind of aims. Another limitation that was present in the ADRACLIM project, that in the ADRACLIM Plus we somehow corrected, is that we didn't consider in that project the remote sensing, while we know also from the EOatSEE project that this is an extremely important component. We know that there is so much information that can be taken from airborne observations. And so in the ADRACLIM Plus, we have a dedicated chapter in this respect. So still, what are the ambitions of this project? What are the innovation aspects? Is that we want to enhance our ability to perform an integrated climate modeling, but also, so essentially we want to keep the architecture of the modeling chain that we developed in ADRACLIM, which is one of the strengths and of the innovations in the ADRACLIM project, but we also want to decline it in a multimodal way, so that we are going to develop an ensemble and being able to quantify the uncertainty. And also at the same time, we want to further enhance the observational capacity. And here we are going to invest in this respect, both on further improve our observational network in the say for about the field measurements, but also here we have a special chapter related to remote observations, and we have people skilled in deriving innovative procedures to get observations of various phenomena from satellite data. In particular, there is a focus for what regards the remote sensing in this new project on sea surface temperature, sea surface salinity. So I'm not now a satellite guy, so don't ask me how we can get the salinity from the satellite observations, but I know there is research ongoing to be able to do that. But also for biogeochemical quantities like chlorophyll near the estuaries, where there is really huge uncertainties in the observations that we have now. And this will be done with a special focus to estuaries. And okay, I'm not part of this, I'm not, say, involved in this part of the research, but this is to show that the team that will be working in ADRACLIM Plus about this is very skilled in this kind of operations, and will be able also to quantify the solid particulate matter and the suspended sediment, the dissolved organic matter, the chlorophyll, especially in estuaries and coastal shallow waters. And that's all about these two projects.
And that's a lot, Lorenzo. That's a lot of interesting advancements and prospects for the future here. So I see a lot of very interesting work being done in the Adriatic. So I guess we can start by addressing this question. I have a question from Pedro Almeida actually in the chat. Maybe Pedro, you can repeat the question live while Lorenzo comes back to the slide where you found the information. Just
okay. Yes. Lorenzo, thanks a lot for the very nice presentations and quite impressive amount of work. I was wondering in the project where you look at the influence of circulation in the Adriatic Sea, and that you show this very large number of dots, red dots with catchments. I just wonder if these are dots related with river discharge observations, or is this from the model that you mentioned? Just to clarify a little bit of what type of data did you use for this?
So I believe that these were all the catchment areas that, or maybe no, I think these were the station data that were used to validate the model. Because you see the catchment areas are this one colored in different colors. Okay. So essentially, these data were validated using station data.
So these red dots are the station data.
I think so. I think so. Okay. Yes. Yes.
Okay. I was just curious about that.
You're welcome.
Thank you.
Okay, I was just checking if we have any other questions right now in the chat. It doesn't seem so. Let me just check on YouTube if we don't have anything coming from there. No, not yet. Okay, so with that, we close this part of our workshop. And what we can do now is wrap it up with some reviewing a bit of what we got in terms of feedback. So I will start by sharing my screen and just showing a little bit what we're going to do next. Minutes. And as you can see, once again, I have here the link to connect to this online pool. And the reason for that is that we are going to keep this live pool open. It's not longer is going to be a live pool. It's just going to be a pool now. But it will keep it open to actually keep collecting this feedback. We have a set of questions. Some of those are open questions, so it's quite interesting what we can get with that. A lot of times with these online events, it's hard to get everyone arranging their schedule to be at the same time in the same room. But then on the other side, of course, we have recorded the full event and we have published it. It's already published in YouTube on real time. So we'll make some more communication actions in the project, in the partners, social media, and try to ensure that we can get as many answers as we can. Because here are our next steps. Basically, this scientific roadmap will become a document that will be part of these deliverables that we have in the project, and it's going to be delivered by the mid of June. So we still have some time, and we are going to leave this pool open at least until the end of May. That's the idea, that we can, until the end of this month, still send the survey for a lot of our contacts and stimulate them to provide us with feedback, with, of course, relying on the recording of the whole workshop as a reference. But beyond that, we are also going to revisit some of those requirements that we're gathering in the initial phase of the project, the requirement baseline phase. And we are going to revisit that, of course, as part of our project. We need to provide some traceability and look back to what has been accomplished in the project, what we were able to address in terms of those requirements. And of course, those that were not fully addressed will be migrated directly to the roadmap. Also, we are having, and we are still having, a lot of discussions among the consortium, also with associated scientists from the partners, from other institutions that we've talked during this project. A lot of these product providers, a lot of these products that you see today are based on recently developed and released data sets or products like the extract. So we were in close communication with the teams that developed those projects along this whole project, and we are going to get in touch with them once again and make sure that we can learn from their past experience and gather more requirement, more information that will drive the future research. And finally, we're going to review also all the information that has been published during these 2 years of the project that we didn't have access in the beginning, in the requirements baseline. Now we will have, of course, newly published documents and material for instance, from Coast Predict initiative, but even from other climate that Lorenzo just showed. So I'm sure that we will be able to find a lot of new insights that are coming from this project, just because we all know that the science is moving so fast and is just transitioning to operation very rapidly. So it's very clear that we'll be able to find more interesting insights there. So I'll stop sharing this one now, and I will share one more piece of information. Just to remind you that we have this special edition that Lorenzo and Pedro were talking about some minutes ago. So as you can see, this is already open since the 9th of May, since last week. It's open for contributions, but we have a very long deadline. Actually, it's only for next year's February, so that you can convey here all your new work that is related to how to apply Earth observation to extreme sea level events. And of course, coastal risks, coastal impacts. We are now compiling this, waiting for this publications to be compiled. Of course, everyone that is from this community is welcome to contribute, and also welcome to share this opportunity among your peers, among your colleagues, because we think that there is something very interesting to be built here. Our project will be kind of a baseline for this special edition. We will have a white paper just related to what we're doing here, to the roadmap for future research. But then we also have some very interesting technical papers from specific aspects that were presented here today, during the day. So this is another invitation. And finally, we'll now show the results of our ongoing poll. Like I said, these are not the final results. We are still going to have many more answers coming, hopefully. But right now, we had around 20 people answering the poll, which is almost everyone that we had here in this webinar. So it's a good result, but I'm sure that we can make it better. As you can see, we have some good distribution, but of course we have some concentration here over Europe in terms of who is watching us. I'm pretty sure that there's also the time zones here making some influence. So during the next 24 hours, I expect that this map will have many more dots. Let's hope. Moving on, here is the world map that we were trying to build, some ideas, the first thing that comes to mind. And as you can see, of course, some negative expressions here, of course, flooding, destruction, hazards. But on the other hand, also the solution, it seems to be here. So monitorization, numerical modeling, data adaptation, early warning. I think that's all interesting expressions and help us understand exactly who we are talking to and what are the main concerns of this community. Here, it's again, it's still on the profile of our audience. As expected, we have most people coming from academia, because of course this is a scientific workshop. It's not really intended to be shown to end users and decision makers. Of course, they are very much welcome to participate, but as you saw in the presentations, it sometimes goes a bit deep into the science in the more technical aspects, which I'm sure that are very interesting for the scientific community. So again, very nice result. We still have participation from all those sectors, even if there's this predominance of academia. Here we're taking a look at different parameters that can be generated using EO, using Earth observation, and on the x-axis, we are trying to see what's the opinion of our audience about the usefulness of these different parameters, and on the vertical axis, you can see what's the familiarity that our audience has with these algorithms that generate these parameters. So we can take a look that it's very heterogeneous, the answers actually. I think most people think bathymetry is very useful, but maybe the literacy about how the algorithms work is not yet there. Similar results for topography, even more limited knowledge about how this works. Of course, land use, land cover, maybe that is a more conventional parameter. People are more used to see this coming from Earth observation. Of course, sea level, here also good amount of people with very high numbers, so thinks it's very useful and also knows it very well. And similar result for waves. Flood maps, a bit more distributed. So this is, of course, some results that will get even more clear once we have more answers. And as you can see, most people think all of these parameters are quite useful. Maybe this one is the one that we cannot have too many solutions come from EO. So that's why we have a bit lower numbers here. So the idea here is to be dynamic, so feel free to interrupt me at any time with questions or comments about these results that we're showing. It's really just the idea is to have as many participation as we can. And here we are trying to understand what's the opinion of our audience about the usability of the usefulness of this Earth observation for coastal risks. So everyone is quite optimistic that this will become more and more important as we progress in this more data-driven technology that we've been developing. And here I think I see a very mixed answer. Can we make something that is a long-term dream from the numerical modelers that is basically cover every single stretch of coast around the globe with very high resolution models that can provide us with the forecast? I see this is a very mixed results, and I think I expected this because we are currently really on this transition from numerical models, physics-based, to something that's more data-driven and probably less hungry in terms of computational power. So that's what we expect, at least for the forecast. So interesting answers here. Next one, a couple ideas about what is still missing. So this is the final question that I had in this initial part of the survey, where we were trying to be very generalistic, trying to understand really what are the open-ended, what are the gaps of information that we think that are still to be fulfilled. So yes, bringing these waves to the coast in terms of sea level, it's a challenge. I must say this is one subject that we've been discussing a lot in these projects. Of course, we have a very specific product in EOatSEE, the coastal water level, that was designed specifically to address this. But we all know that it's based on Stockton, but has limited effects. And then, of course, depending on the type of the coast, it can still face a lot of problems. So there is room for improvement here for sure. I guess the topography products for small island states, that's another thing that we were quite excited. Is the presentation that we had this morning about Marshall Islands coming from Mateus showed that we were actually, I wouldn't say surprised, but happy to see that the results of these EO-based solutions, when applied to risk assessment, for instance, they actually surpassed our best expectations. They were actually very, very close to the results that we were getting when using very high quality in situ data, the LiDAR data that they had for that particular use case. Not in situ, but LiDAR remote sensing. So quite interesting results, and we of course agree that it should at some point we should target this objective of actually providing this data for several different small island states, isolated small island states. Of course, good quality data for bathymetric. That's a desire that everyone is waiting. I know there are a couple initiatives ongoing on that. We just saw Rafael Amar presenting his product, but there's also other products coming very soon in Copernicus' new coastal service. Time sampling from EO. This is an interesting subject, and I think it deserves a comment. Because indeed, a lot of what we've been showing today, a lot of what we've been doing, it lacks the substantial temporal resolution. A lot of times you'll get the information only once per week or even less. So we all know this is a problem. It's a very strong limitation of Earth observation. However, we also know that the pace in which new platforms, new sensors are being deployed, are being launched, is growing exponentially. It's really, really fast. So we expect that in the upcoming years, we will have much shorter revisit time, much better temporal resolution, but even better spatial resolution and coverage. So the lack of EO data, it's something that we all know that is not going to be such a problem in maybe another 5 years. So I can name one example, that is the Atlantic constellation currently being developed both in Portugal and in Spain, that will launch two, 3, 4 different constellations, which will provide real-time or near real-time monitoring in the Atlantic. And the design is to try to have the new information every 3 hours coming from for the whole Atlantic basin. So it's quite ambitious, but this is just one example, and there are many others. So this is a problem today. We all recognize it, but it is a problem that it seems that it's going to be diminished. I wouldn't say solved, but it's not going to be so important in another 5 years' time. Interesting comment here about converting this data into energy resources. I have worked with this personally in some time ago, so I think it's an interesting example where climate mitigation and adaptation comes together. Of course, we are all trying to retrieve this data and work on these algorithms, always thinking about climate adaptation and coastal risks and climate resilience. But on the other hand, if you have better data, better information, you can also access much better these natural energy resources, especially in the ocean, of course. So it's an ongoing trend, very fast moving, especially in Europe, to produce the energy in the ocean. So I think that that's quite a good prospect also. And then we have ocean color product, high resolution. We didn't really talk too much about it apart from bathymetry, which is an ocean color product. But maybe here what is more related to water quality is not something that we are really addressing in the project, but of course it's also affects these coastal managers, and it also will benefit from this growing number of satellites in the near future. So it's an interesting outcome also. Okay, next answer. Let's now talk more specifically about the products and presentations. So this is from the first presentation we had today, which is about the EOatSEE own coastal water level product and how the audience evaluates it. So it seems to be very useful if it works. It's not so hard to be explained, which is also something good for the users for sure. It is quite innovative in terms of putting this in operations. Of course, some of these analytical models are known for a long time, but now we have the observation data enough to actually build an operational product. And we see there is a very large potential to integrate the solutions in this, in the work of these researchers and managers that we have in the audience. Also about the same product, what are the strongest limitations? What are the barriers to actually use this product? And here also quite interesting results, because we know that I just mentioned temporal resolution, the visit time is a big problem, which was addressed by the product. The product combines data coming from a lot of different platforms. So in this way, it minimizes a bit this problem, but still we have, depending on the site we are, it can be from 1 to 3 days to have this visit time. So it's, I would say for flood monitoring, it's still quite complicated. But on the other hand, this is a product that has some latency. It takes a while to be delivered. So this is another aspect being highlighted here. Something to be improved. It's a long supply chain right now, because like I said, it's depending on several different platforms, Topex and Sentinels and all the different platforms that we have, each of them with their own ground segment. So to reduce this latency, I would say it's quite challenging with the current landscape. Of course, when we're talking about future constellations, we can then discuss other options. For instance, onboard processing is something that Deimos particularly is working on, and it's very promising in terms of reducing this latency for the products in the future. But then, of course, the largest problem, and it's the trust, is actually to trust this data, to actually believe that this data that is originally measured quite far from the coast can actually be translated to the coast regions, and even include the wave effects on it. So this, of course, demands more benchmarking, more validation, more testing. I think we went a long way into EOatSEE. This was a central product from the project, but for sure there's still room for more people to test and evaluate this. And we would love to build partnerships to do this kind of benchmarking. Again, just interrupt me at any time.
Yeah, Pedro, maybe.
Yeah, I have a tendency to speak too much, Pedro Almeida.
A little bit. No, to let you also rest a little bit. But before, related with this previous subject, I think from maybe the point of view of benchmarking or validation comparisons, maybe the lack of information is still on the coastal region regarding the wave process. So the wave run-up, wave setup are still the ones that probably are less calibrated or validated or even benchmarked. While, for example, to have a tidal gauge or a wave buoy, although there are not many, they still exist, and there are networks that aggregate this information that can provide you with a certain let's say standards of quality. While, for example, you can't really find a similar network for wave run-up or wave setup. that does not really exist. There are a few probably coastal stations doing this for a longer period of time, but very little ones or a little amount of them are constantly acquiring data and providing these data sets for these accuracy assessments or even to improve the existing parameterizations. So I think if maybe if I could guess what is behind this fourth responses here regarding accuracy, I would say that the one that is less assessed is the wave process induced at the coast, while the others are I think they are still going. This one still I think still needs quite amount of work to improve our understanding and our capacity to improve the predictability. So yeah, and also this also make when you show the first answer, I was also thinking about what type of audience was responding to these questionnaires, because I saw basically that people saying that Earth observations are in fact a very good data source, but I was curious about, yes, exactly this one. I was curious about seeing this last, let's say, forecast capability in the front of the traditional numerical modeling approach and process-based approach. Because what actually the project has shown to us is that there are many nonlinear interactions at places like Madagascar, wave current interactions, or in estuaries where you have also wave discharge, river discharge and tides interacting with waves, that they are nonlinear and actually quite difficult to resolve without a numerical process-based model. So I guess the people here from CMCC modeling, and they probably have a different opinion, or they are also exploring the AI. But in fact, you need to combine the two, I think, for getting better solutions, because without this model and this understanding of this process, you can't really find I would say you can't really probably even measure it, these type of interactions with Earth observations. So you actually need to predict well the total water level at the coast and so on. You need to deal with this process. So you actually need numerical models to do that. So I was curious about the audience because of that. I was actually, maybe there are not too many modelers here, and probably a little bias on the AI and the Earth observations, but this is also a reality.
Yeah.
But anyway, I was just commenting on these points.
Yeah, looking at the result now, as you can see in the numbers that we had, in the votes that we had in each number, actually this is quite in the middle, because we have 3 people that thought that this is not very true, 3 people that thought, okay, this is true, and then 4 that just voted in the middle. So I think people are not really sure. I think here it's I agree with you first, Pedro. I also think that the future is looking like some kind of mixed hybrid solution will be probably the best way. But on the other hand, I think here also AI is a buzzword. I think a lot of people talk about this. Just a couple weeks ago, there was this very large new meteorological model released by IBM, which seems to be outperforming every meteorological model in the world by far. So it's something that nobody was really expecting, and then it was just released like that. So I think we are living in a very special time for this predictability kind of science, because we're receiving contributions from a totally new community. People that have never worked with the environmental sciences are now coming to this topic and bringing very core IT solutions. So I really am not sure what is going to happen. I think that's going to happen. There will be some transition. There will be much more usage of this data, of these observations that we are getting more and more. And some kind of hybrid solution will become, depending on the scale, it will be more leaning towards AI, more leaning towards physics. There are a lot of good AI techniques to cope with non-linearities. So even that is not really a limitation if you have enough data. So I think there will be some surprises. There are things here that we know, but there are also a lot of things being developed in private that we don't know. And as everything else in AI, it just develops very, very fast, surprisingly fast. I think we were all surprised with large language models last year. Maybe next year we'll be surprised by very large predictability models for environments. So I don't know. It's just a food for thought. Just to comment on your previous topic, and I will open for Lorenzo to comment on here on the AI topic, but just to comment on the run-up thing, I think you cracked the code there. The problem there is not only that this is physically a difficult process to represent, because of course it's very much affected by morphology, and if every little change in morphology will have a very large effect on wave run-up and setup. But also it's, and that's your point, it's something very hard to measure in situ. I guess today probably the best technique that we have is through cameras, like Mahika actually showed in her presentation this morning for the Dutch coast. But that, as you said, it's very limited in terms of sampling and where it's available. And then if you are in just one type of environment, but you move to a different kind of beach, it's already not valid. So indeed, that's a limitation. And another thing that will depend, so there's still a lot of need for in situ measurements on specific, very specific topics that we are still to uncover. Yeah, Lorenzo, maybe you can say a few words about the work you've been doing with AI, the approach. I know that you actually trained your AI model with a physics-based model, so it's already a hybrid approach in that sense.
Well, yes, indeed. But if you see all these models that claim to outperform the physical models, in reality are trained using physical models, because you don't have in general enough observations anyway to be really able to train a data-driven model. And also, if I may add something, so in general, the approach that is used today is in general hybrid. And if I may add, the knowledge of the law of physics and of the law of dynamics is in reality puts a very strong constraint on how this dynamics works, this phenomena works. And in my opinion, a very efficient approach would be the development of an AI model that knows that the laws of physics exist, and that doesn't have to learn every time from the data the laws of physics. I mean, we know the laws of physics, so there is no point to relearn every time everything from the data. We should, I think in the future they'll do it. We'll still use an hybrid approach where the AI knows that there are the laws of physics and learns using them. This is my personal opinion.
No, I couldn't agree. That's what I meant when I said that it's an AI model constrained by the physics, somehow limited by the physics. But again, I must say, this is evolving very, very fast, because this sort of model, I have already heard about it. There's already a lot of people starting to work on them. So let's see what we're going to have, but maybe we're going to have some news from Silicon Valley, or I don't know. Let's see who gets there first. I know that we are in a very good spot in Europe. Mahika, please go ahead.
Yeah, just to state again the use of remote sensing here. So we have these kind of models like XBeats and Sphinx, where we do start to predict flooding, as you know. and we are really helped with remote sensing data that shows this actual flooding. So actual coastal flooding, just to see where the model performs well, where it performs less. So if you have the remote sensing data, we can start comparing it with the model, seeing how does the model perform in the beginning of the flooding? How does it perform when the flooding retreats? So these kind of things are really interesting also to check the models. So just to say that AO does play an important role here as well.
Yeah, indeed. Thanks for reminding this point, of course, Marika, that we always used in situ data for this setup and validation of the models, but now we are very prone to use EO, just considering the availability and the coverage that this kind of data has right now. And thanks for the Copernicus programming for that. Probably a lot of the work of making these things operational and stable that were done in the past decade is now actually resulting in these advances that we are discussing. Okay, so that was a nice discussion. Here where I'm gonna take back. Are you, just to confirm, Pedro? Can you confirm we're still seeing the survey? My theme with the survey.
Yes.
Results?
Yes.
Okay,
Yes.
just because I've been changing the screens and just to make sure. And indeed, now what the value could be coming from that total water level product. In this case, we had very similar answers actually for all these three questions. So people seems to be very interested in having this historical product with a global coverage. This is something that we're actually planning to do in the future. We're making way to that, and let's see if we get that very soon, or if we have to wait for new funding. The idea here would be, the second idea would be to have an operational product, to actually have this tiny series being built as any other operational product, for instance, those that we get from Copernicus. So here again, people seem to be very interested. And then finally, I think it's important to comment that this total water level product is really looking to the historic context. It's not a product that can provide by itself forecasts, just because this is, of course, based on observations, and there is that latence that so there is this difference between where the data is captured by the satellite and the data in the time where we actually get these results. Today, it's quite an impediment for a near real-time product, just because it's coming from so many different platforms. So what I had in the third question here is, again, considering this conversation we just had, can we build some kind of model that uses these observations to train some AI algorithm, but then with the constraints of the physics that we could include in the model, it could provide forecasts and actually provide this short-term forecast using the behavior from the past. So basically looking at what is happening offshore, away from the coast, and with that information trying to understand what's going to happen on the coast, but also next week. So not only changing this, downscaling it to the coast, but also forecasting it for a couple of weeks. So this, I think it's exactly what we've been discussing before. And there is for sure a need for it, and people are asking for it. Here we just had an open question, the final question about this EOatSEE coastal water level product, and the only answer we get is that we need some collaboration and training, and of course that this project, the EOatSEE, was not intended to generate or develop any operational products. It's just a benchmark and a proof of concept of some solutions that were conceived. So, but of course, if this is going to transition at some point to an operational project, or even for just a full stack global coverage 20-year-long product, then the documentation would also need to be produced to provide enough information, and eventually also training should be provided. So transitioning now to satellite-derived bathymetry and topography, I have asked here what are the main limitations, and I guess that this was accepting multiple answers, but it seems like it didn't, because it's just so similar, the results. So I might have make some adjustments. But indeed, here again, uncertainty in bathymetry and topography derived from satellite is a known issue. It's something that, of course, it's been improving as we progress. We demonstrated today the difference of having a commercial, very high resolution imagery as an input. Of course, you get much better spatial resolution. The images that Mateus showed this morning had a 2-meter spatial resolution, which is already quite interesting. But also had a very large uncertainty still for some applications, maybe for others not so much. But of course, we cannot conceive any port or transportation needs here, because of course they must be very precise and reliable. But we're making way. It's getting better. Here also range depth limitations, another very known issue from topography and bathymetry. In this case, not topography, only bathymetry, of course, and which changes a lot depending on the environment. But in the case of Majuro, of course, very clear waters, we can have a very long range, but then on the other hand, uncertainty is affected by a very heterogeneous seafloor substrate, which of course has very heterogeneous albedo that are reflected in this larger uncertainty. So different environments, different problems. The spatial resolution I just mentioned is something that maybe people are saying it's a problem because they're thinking about Sentinel-2. But if you go for very high resolution, I think 2 meters, it's already very good resolution for a bathymetric survey. So I think it's also quite interesting. And still a couple of people talking about the availability of this solution, which is of course very limited companies that are still already offering this as an operational solution, a commercial, and the price of imagery if you go for commercial imagery, of course. Okay, I will transition to the next one. Please, like I said before, interrupt me at any time or use the chat if you cannot speak. Regarding DTMs, I was asking how much people are aware of their availability. I didn't make the question specific for Delta D DTM just because it's such a recent product. But then, of course, a lot of people might not be aware. But it seems that most people are aware that this kind of products are out there. And about the adequacy of this product for coastal risks analysis, very heterogeneous response here. It seems that some people are already satisfied with the current resolution. But then if I ask if they are happy enough to replace the in situ surveys, then it's a clear no. The answer is a clear no. Which I must agree, because I also think that for most applications, it's still not at the same level. On the other hand, the satellite-derived bathymetry and topography, it provides us with something that is quite useful, which is the revisit time. You can actually have this build long time series, and even with a large uncertainty that can lead you to understand the processes and the changes in a specific zone. So I guess this is the advantage, but the disadvantage is really the reliability, the accuracy. It's still not there. And yes, that's the duality I just showed in these last two questions. So from one side, the accuracy is not there. From the other, revisit and update of DTMs, it's really, really good for risk vulnerability assessment. We can think immediately of an example of a pre-storm, post-storm survey, which immediately gives us a lot of insight on how this coastal morphology is responding to the extreme events. Okay, we're almost there. Rank the parameters. For calibrating and validating numerical models, I must say to have topography here as a first is kind of surprising, maybe because people were thinking about flood. That's probably the reason for having topography so high in the list. But then, of course, you have waves and bathymetry, which are the usual suspects, and sea level as the third, as the others here with more important. Quite an interesting result also to check, and very much in line with to the conversations that we had during our project. I think most of the times that we tried to use the river discharge, it was not totally feasible, I would say, because you're not really measuring it from EO. We are just, you have to have these stations in situ, which are not available everywhere, of course. And we also had a couple challenge. It was quite a big challenge also to integrate vertical and motion conversation within or scientific use cases. So this result is pretty much in line to what we expected, I would say. And this is actually my final question, and I think we're gonna very soon receive more answers on this one, because we only got one answer, which is in open questions usually get less answers than the alternatives questions. But like I said before, we are keeping this open, and we are going to distribute this pool to a wider audience and reinforce with the people that were invited for today's workshop. So I'm pretty sure that at some point we'll enrich these results, and which will all be compiled and be a part of our scientific roadmap documentation. Well, that was a lot of talking on my side. I think as a whole, the event was quite rich in terms of conversations and discussions. And we are, of course, very interested in hearing more from the audience. So don't limit yourselves to this pool, which is being shared, but also you're welcome to connect to EOatSEE. Visit us in our website. You'll see there's a contact form there. There's another link also for including your very specific user requirements. And I didn't send this link today because it was just too many links. So just start by going to the EOatSEE. After you fill up the pool, just start by going to the EOatSEE website and reaching out to us, and we can start this discussion. We are very open to discuss, to collaborate on this last couple months that we have in this project. This is a long-term conversation for all of us here. We are pretty sure this is going to be one more, but there's going to be many other projects in the same subject for all of our group here. So reach out, and we'll be happy to talk. Okay, I don't see any new questions in the chat, not here, not in YouTube. So if anyone wants to make any other comments, otherwise we can probably close the session, which is almost time anyway. Okay, so I will close now. Welcome once again for all the participants for being here, and welcome also to the others that are watching this, not live, but on the recording. Your contribution is very important for us, and we'll be hearing soon from us also when we conclude our project in terms of we're going to make more communications about our outcomes and make them public on our website. So we'll also be able to assess the technical documentation from the project. As soon as this is available, we'll make sure to communicate it through our social media and the Air Center network. Thanks very much, and see you on the next event.